but the new name for this endeavor is the Consortium on the Landscape of AI Safety. So what are we talking about here? Why do we need something like this? So we're all interested in this field of AI safety, but what is AI safety? What does AI safety entail? What are the relationships among the constituent topics? For a given type of use case, what safety considerations or methods are there? These are just some of the questions that this type of endeavor hopes to answer. And these types of questions make it clear that, in fact, we all come from quite different perspectives when we try to answer some of these questions. So, in fact, the field is an amalgam of hundreds or thousands of different kinds of ideas and concepts, different methods and methodologies, where each of us are exposed to a subset of these. But really, the field broadly is much larger than that. And it's very interdisciplinary. So this includes safety engineering, assured autonomy, trustworthy AI, responsible AI, some aspects of ethical AI, and control theory, and longer-term AI safety research, human-computer interaction, decision theory, etc. So we all come from different perspectives, different sets of fields. There is some impetus to mutual understanding. In part, this is coming because the actual technologies are converging a little bit in some of their capabilities, some slow march toward generality that we're seeing. But really, it's also because the community is growing, and we're sharing more amongst each other as well. And this is hoping to push that quite a bit. So we're hoping to promote the awareness of how to create, test, deploy, operate, evolve safer AI systems and autonomous systems. And one should note that there's also a growing impetus for auditing these types of systems. And so making sure that one has all of one's bases covered is also an important consideration that is driving this kind of need. So having an actual landscape would also help to bring to light additional trade-offs inherent to certain classes of systems, which might otherwise be overlooked. So we're contextualizing the broader technical, strategic, ethical, and policy issues within all of the aforementioned very specific tactical research and engineering issues. So we're looking to map the territory. So historically, this mapping of the territory has been done mostly by research agendas and survey papers. These, of course, are fixed points in time. They're relatively narrow scopes, representing many compromises because they're representing a single taxonomy, typically. Examples of these, quite good things, quite useful things that we want to embrace and extend and understand how they help to bring us where we are today, are some of these I mentioned below. So like the DeepMind taxonomy, Assured Autonomy International Program from York University's body of knowledge is absolutely great. Future of Life Institute put forward a landscape of technical AI safety research in 2017. I'll highlight in the next slide a figure from Tom Everett and folks that are very useful here. So we're looking, again, at the growing topic area, AI safety, trustworthy AI, responsible AI. And so before 2020, we did start a series of workshops, of which this is part of the series, at IJCAI-AI-Safety and AAAI Safe AI, as well as WACE. There are also, of course, related workshops on AI safety at NeurIPS and other conferences. In Macau, and actually IJCAI as well, there was a panel discussion where we were trying to iterate on how to approach this need for the landscape. And what came about was a suggestion that I made for having this sort of multidimensional knowledge graph-based system that could sort of dynamically slice and dice different conceptions and different relationships. Briefly, before getting into what came of that, here on the very left, we're seeing this FLI landscape. To the very right, we're seeing that DeepMind taxonomy that I mentioned. And pretty interesting in this Everett paper at the bottom here is, I think, one of the first, or probably the first type of mapping among the different taxonomies from different organizations. And when I first saw this a couple of years ago, I found it to be super like useful and super interesting, trying to line up the different conceptions that different people, different organizations have about the space. This Everett paper is focused mainly on sort of AGI and sort of longer term AI safety, but one can also appreciate how this would be relevant to extending this graph to shorter term considerations and present day systems as well, which again are not mutually exclusive with the longer term systems. There's still quite a lot of overlap among them. And so that's one of the things we'll be addressing soon here. So in 2020, in February, we had a meeting of about 20 different organizations. You can see them at the bottom of the screen here in New York City at Bloomberg's offices, where we were talking about this need, trying to make some progress. And so we were iterating quite a bit on specific taxonomy, but also realizing that there are different views on the taxonomy, and there are different ways that we can fit in different subtopics and topic areas, that actually we do need a system to connect these different views. Some of the history of that and some of the minutes for that you can see at AISafety.org. And in that meeting, I was nominated to lead the effort, and I accepted. So from that meeting, the organizers of that formed a provisional board where we were iterating more on the default taxonomy, as well as what governance mechanisms we could use to have these different parties collaborate well and safely. And also working on the platform, on that software where people can actually collaborate. So frankly, a lot of 2020 was exploring these options for legal entity and iterating on the right kind of architecture, the right architectural plan for this. We did get a volunteer in each of governance and technical development, and so that was super helpful. So what we have now, as of January 1st, is a member program alliance, or an industry consortium under the IEEE ISTO. The ISTO is the Industry Standards and Technology Organization. It specializes in helping to stand up and helping with governance and administration of industry consortia. So it's a formal consortia, and this is very useful in giving companies, especially commercial enterprises, a lot of comfort in the way that the consortium is governed, because there's so much experience in governing other consortia, and we're using those learnings from ISTO in structuring those governance documents that we're finalizing this month. So various kinds of IP protections, various kinds of other clear rights and responsibilities for all types of entities to be able to enter into this collaboration. The founding board members, you can see here, we have 6 of them. We are open to 1 or 2 more, as well as a whole host of other members who will be contributing to the CLAI Knowledge Graph. So CLAI Knowledge Graph is something that will represent quite a variety of different topics. You see here process and assurance, algorithms and architecture, theory and implementation. I don't need to read this whole list. So pretty much all the different granular topics across the superset of what you might consider to be within the AI safety realm. This knowledge graph will consist of multiple constituent sub-knowledge graphs, which are themselves typically directed acyclic graphs with some potentially undirected components as well, but still maintaining acyclic constraints, where there is sort of a progression you can think conceptually from left to right, which I'll show later, of from general to specific. So the Clay Knowledge Graph system is a software as a service and repository for holding this knowledge graph, for exploring it, for editing, for doing curation, and for rendering outputs. And of course, we hope to open source the software and put the content under Creative Commons. There'll be integrity checks as each linkage is created, as well as very contextual permissioning. So I'll get a little bit into the types of outputs, which I'm sure you're all interested in a little bit. First, the ontology here of what we're talking about in this knowledge graph. So there are concepts, application specializations, technologies, and applications, which I guess I should have put before the specializations there. Connecting these are what we might call primary hierarchical types of predicates, which form the primary structure of the graph, as well as secondary predicates or secondary connection predicates. So these component of, hyponym of, application of obviously go from are unidirectional in terms of generality and specificity. So why do we need these constituent views? So regarding centrality and hierarchy, framing, the content of concepts and methods, we have different perspectives. I found this when creating that Future of Life Institute knowledge graph in 2016 to 2017, when trying to get a variety of different, lots of different people with lots of different perspectives to agree on a single tree, a single taxonomy. There were a lot of compromises. Nobody got exactly what they wanted. It's a useful thing to do, to find where those compromises can fall, but it's not always the most efficient way for everybody to get all of their views out and connected to each other's. So really, when we look at AI safety, it does consist of all these different fields, and these different fields, these different disciplines often use different terminology. So damage and regret actually used quite similarly often. Safety reserve versus margin of error versus treating risk, or safe fail versus fallback. Value line, I don't need to read all of these, but you can see that these are just a small handful of examples where indeed there are very similar concepts with different terminology from different fields. So different organizations bring their different perspectives, different fields bring their different perspectives, but also the different individuals, even in the same organization, in the same field, can hold different implicit schemas of the topic, informed by what they were exposed to first, and what they learned on top of that, etc. So there's some ordering bias there as to just how their internal ontologies are created. So we want to enable the full expression of these, because none of these are invalid, actually. I mean, the way that we think about things are typically for a reason. And yes, we can collaborate on trying to harden some of these views, but there are legitimately different parallel views. And so at the level of the organization, we really like to invite organizations to contribute these perspectives, these views, these maps of the space, and indeed to put their own stamp on them. So the topics in scope here are AI safety foundations, specification modeling, verification validation, runtime modeling and enforcement. So again, all the types of things that you might think go into this space. If you're looking at this list and you see, or you see the lack of some high-level area that you're involved in, please don't hesitate to reach out and point it out. So among these different perspectives, there needs to be also a catch-all, so sort of an other. So we're calling this the Clay default taxonomy. This is for sort of one-off contributions regarding a small number of topics. This is a scaffolding on which they'll live. It's not a primary view, but it is a very useful utility within the system as well. So this is a current view of it. This is not the final nor the proper, or it's not the actual system view of it. But one thing that this image is illustrating is when selecting for, in this case, high-level concepts that are essentially the roots of the multi-tree, we can see how those have relationships downstream in terms of their more specific things, which again, because this is a directed acyclic graph, each child can have more than one parent. And of course, each parent has multiple children. This is a slight zoom in of that. So again, covering pretty much all the different types of considerations in this space. In terms of outputs, part of the point of creating this knowledge graph system is to have rich outputs that are very, very useful for a wide variety of stakeholders. So the constituent elements of those are trees and networks and lists. But really, when it comes to the useful outputs, okay, sorry, jumping ahead there. So in terms of network graphs or graphs of any kind, so epsilon here simply means the empty string. So basically directed graphs, undirected graphs, and mixed graphs. So at the left here we have sort of the precursor of the Clay knowledge graph system, which is in terms of the technology, the FLI landscape. And I should note quickly that it's a precursor because in the knowledge graph that was actually constructed in a similar way, where there was an underlying data structure, and the visualization was constructed in tandem with a rendering of a document, a document that looks a lot like any other survey paper that you might see. So again, this is an actual data structure that was authored by me at once. And then this program would generate both types of outputs from that same data structure at the same time. And so really we want to take that idea and extend it to the nth degree with the Clay knowledge graph system here. On the right here, we see the beginnings of some mappings between different perspectives on the space. So in purple, we have the FLI graph. In pink, we have the the Clay default taxonomy. We can see some of those different types of predicates coming into play, and some of them are directed, some are undirected. Here we have a little zoom in of that. Don't worry about the actual details of it necessarily just yet, but know that they are there. So other very important types of outputs are document-oriented outputs. And so really fundamentally in terms of the queries, these are trees. since each node is not just a name, but really it's a rich set of semi-structured information, which include sort of inline references, different levels of explanation about the given topic or idea, and of course the different linkages which are also described between the different nodes here. So specifically on the left, we're seeing an early prototype of the Clay knowledge graph system, actually generating some document-like output. On the right, again, from the precursor, same type of similar type of system generating a table of contents here within a PDF. And on the left, the actual document content from that same system that was generating from what really is a tree in that conceptualization. And then we see up top a tree and then below a tree. Now, when we have a directed acyclic graph, it's not quite a tree. So we actually are developing algorithms for intelligently chopping that up into a tree dynamically as needed, which can render tree-like things that need to be flattened out like documents here. So in total, checklists, syllabi, mind maps, guidebooks, research agendas, gap analysis matrices, which are super interesting, and I'll get into a little bit later. Or you know what, let me get into them now. So the fact that we're doing these correlations between these different perspectives actually enables us to make a literal matrix of what these different perspectives are saying about high-level topics, and using the details to fill in matrices where, based on the connections between these different perspectives, we can say that this given type of consideration at a high level is not addressed by this other taxonomy or this other map of the landscape, since there are no appropriate linkages of the various of the given type that would imply that there would be. So because we can see these white spaces within a given taxonomy or a given map of the space, it's a super useful tool for finding unknown unknowns in one's conception of the space. And this is something that actually came up in our last Puerto Rico conference at FLI in 2019. And I actually recommended everybody to make their own sort of landscape of the space. Of course, you know, it takes a lot of time, and so not everybody can, but in terms of an organization, it's a very, very useful thing to do in order to find these gaps and these white spaces and these unknown unknowns. In terms of technical diagrams, we have three variants here: 0, 1, and 2 focus nodes. I think I probably don't have time to delve into those, but it's a very useful way to navigate the diagram. There's also going to be application safety reports where a given type of application area is acting as a dynamic filter on that knowledge graph. And also in toto snapshot of the whole knowledge graph. So a state of the landscape report. So again, any of these output types will be able to be dynamically generated by any user of the system regarding any subset of the system that will enable some great filters to be able to specify what those slices would be. So being a member of the consortium enables members to get perspective on these blind spots and also the relevance of their research agendas and the demand for these research directions. Of course, the connections to other similar taxonomies and other conceptions on the space show some of that amount of demand. the number of references of folks saying that this is a downstream dependency show a lot of that demand. And things that are very related. So again, those rich interconnections among those different perspectives from different organizations will help to inform a lot of that relevance. So this can help to improve the scope and direction of research, and it also enables the safe collaboration, again, with other orgs on this type of topic. It also improves the visibility and eases the consumption of your org's research, because folks can more easily cite it. If you're in something that deals with public outreach or education, it's obviously a great tool for that. You can also, again, create syllabi that introduce content from other perspectives pretty easily. And of course, it helps society by moving the field of AI safety and trustworthy AI and such forward. So if you'd like to join, there's membership@clay.org, which you can email, or you can check out our membership page at clay.org/membership. And at this point, I would welcome questions. So please unmute yourself and ask away. Or if people cannot do that, then
yeah, I think that there are some people who participated in the New York meeting right now. If you have any question by it, I think I'm seeing Douglas. Just don't hesitate to ask Richard now.
Yeah, or if you're not on audio, feel free to enter it in the chat.
Great. Okay, so Mauricio.
Okay, let's continue. I think,
Thanks,
yep. Okay. Okay, we'll continue with the program. We have now a paper presented by Shui Xiao, Jianyi Yang, and Xiaowei Ren, increasing the trustworthiness of deep neural networks via accuracy monitoring.
Yes. Should I present the share the screen, or you will share the screen?
Can you share? I mean, so that
yeah, I can share the screen.
Oh, okay.
Let me find the slides. Can you see my screen?
Yeah.
Okay, I will start now. Hello everyone, I'm Zhihui from UC Riverside. Today I'm going to discuss my recent work on increasing trustworthiness of deep neural networks through the accuracy monitoring. For today's presentation, I mainly focus on these 4 parts. First, we'll talk about what's the trustworthiness for a deep neural network and which kind of problem we are trying to solve here. The second one is we're trying to propose some accuracy monitor for a deep neural network. Then we evaluate our method for different applications. That's the experiment part. At the end, we'll make a conclusion. First, about the trustworthiness of the deep neural network. This is one typical deep neural network inference process for an image classification. Given an input image, we have some model. This model can be purchased or you buy it from some company. It's called a deployed model. It will provide softmax probability for this input. For example, it can predict it's a dog with some probability, say 0.91 for the probability. And here our problem is how to calculate or estimate the deep neural network accuracy on the user dataset instead of the training dataset or the testing dataset. It's some customized dataset. It's easy if we have the dataset with labels. Then we can directly calculate the accuracy using this formula here. It's basically the mean value comparing the label yi and also y hat is a prediction. But in the real case, in the real world case, we don't have labels, or at least some use data we have limited labels. So in this case, how do we estimate or monitor the accuracy? Here we try to estimate the accuracy with the input x and also the output softmax probability, pi. Here we assume that the deployed model, the DN model is a black box model. It's a normal case that DN model are provided by some other vendors, such as nowadays widely used machine learning as a service. So that's our assumption. About the related network, about the related works, there are two kind of related works. First one is the uncertainty estimation. The target is trying to estimate the uncertainty and accuracy for each input data. There are three different methods I would talk about as following. First one is train DNN with the ensemble model, but we assume that the model are provided by some third-party vendor. So this is orthogonal to our works. The second one is they will resample the DNN model, the weights, and create many models using the pre-trained model. But the weights for black box DNN are also not accessible here. For the third method, they try to estimate the similarity between the training dataset and testing dataset. Here, the model is trained by a third-party vendor, so we assume that the training dataset is also unknown. So for this related network, related works, it's required some prior knowledge about how you're training the model, what's the weight of this model. So it's orthogonal to our work. And for the second category of related work, it's a directly accuracy estimation. They will directly estimate the accuracy of DNN model on some unknown dataset. Here are four popular or widely used methods. First one is just a label a subset of samples from the dataset and using the accuracy of this label dataset to represent the estimated accuracy of the whole dataset. This can work when we can label a large amount of data, but if the dataset or the percentage of label data is limited, this will cause a lot of large variations. And the second one is the softmax probability method. It's basically using the mean of softmax probability as the accuracy. The third one is using some function to calculate the entropy of this probability. The fourth one is the time series scheduling. Because the softmax probability, if you use a mean value, it's usually not quite well with the accuracy estimation. So they have some method called time series scheduling. They will recalculate the softmax probability using this formula. For more detailed information about these four methods, you can read the appendix or our paper. So we'll consider these four different methods as a baseline in our work. Then that's the basic background about the trustworthiness of DNN. Let's talk about our method. It's called the accuracy monitor method. Here is one overall illustration about DNN accuracy monitor. We have two parts. The left part is a deployed model. So it's provided by some product vendor, such as you can buy it from some company. The input is for this deployed model is a user data X. The output is some softmax probability. We'll assume it's a black box model. And for the monitor model part, it's actually an add-on part on top of the deployed model. So it can be developed by the customer side or user side or third-party auditor. The input is the inference probability, the softmax probability from the deployed model. The output is for each input probability, it's actually a value between 0 and 1 to represent it's true or false. By calculating the mean of this output, we can estimate the accuracy. As for the model, the deployed model is usually a black box model, and usually it's very complex and deep models. But for the monitor model we design now is a shallow model, contains several layers of perceptrons. So it ends with a binary output. Then about the monitor training, here we have 3 steps to train a model. The first step is a pre-train phase with label dataset. This label dataset is from some public dataset. And the second one is a transfer phase. If possible, we can label a subset of data from the user dataset and then transfer the model. Here it means transfer the monitor model. The third part is the monitoring phase, how to use the model. We'll talk this one by one. So for the training phase, we will pre-train a set of monitor models using some unknown, using some known label dataset. It's called a public dataset. First, we generate the probability on the deployed model. Because we know the label, we can obtain whether it's correct or wrong. It's called a correct-wrong label of the estimation from deployed model. Then we can train a monitor model on the data pair between probability as the input and correct-wrong as the output. Here is a loss function. We use a binary cross entropy to train the model. To increase the robustness of our estimation, here we train a set of model. It's called an ensemble method. You can call it ensemble monitors. Then, if possible, if we can label a subset of a user dataset, we can do the model transfer from the pre-trained model to our to have better performance on our dataset. So here we use the active learning method to label the data. Specifically, we only label the data with a higher entropy. The entropy is from the monitor model. It's actually near probability of 0.5. And when you do the transfer learning, we will frozen prior layers and transfer the output layers, which include the output layer and the dropout part. And with a set of monitor model, then in the monitoring phase, we can predict several accuracies using this formula here. It's basically the mean value of probability, or you can use a threshold method. Here, example method can provide a more robust estimation with a standard deviation because we have a set of accuracies. Then about the experiment part, we evaluate our accuracy monitor on 3 applications. The first 2 are general image classification, including the small scale image, similar to the Cipher-10, and also a large scale image dataset classification for the ImageNet. Also, we test our algorithm on traffic sign detection of autonomous driving. Here is the model, deployed model we use and the corresponding dataset. As for the 10 class classification, we have the VGG16 model. It's trained on the original Cipher-10 training dataset. And for the testing dataset, we have the Cipher-10 testing dataset, Phoenix-10. It's another public dataset. We have the labels. STR-10 dataset and adversary 10. For the adversary 10, it means we generate adversary samples. It's around 100% of the, it's around 50% of the samples are adversary. And here is the results for our method compared with other baselines. It shows that our method can provide a more accurate accuracy estimation. And in addition, here we have the mean value and also the standard deviation provided by a set of monitors. And compared with the random sampling here in the RS, we can provide better performance even than the random sampling with 10 times the label data. Also, we test on 1000 class image classification, the ImageNet. We use 2 models, one is MobileNet, one is the RedNet. Here is the results. As here, the ImageNet A and B is collected from the validation dataset. It's actually have a similar distribution as the training dataset. So not only our method, actually the softmax method can also predict good accuracy estimation. As for the traffic sign detection, we use the German traffic sign detection dataset. Here is the 4 dataset we use. It's D1, it's the original one. D2 is the spatial transform one. OD, which contains 50% image from Cipher-10. And the adversary contains 50% image from adversary image we generate using deep adversary methods. Here are the results. We can see that our method still provides better results. Okay, that's all about our experiment results. Let's make a conclusion. So we developed a multiple model to estimate the DNA inference accuracy. Our method is applicable to black box model. So we do not need to retrain the deployed model. We do not need any prior information about the deployed model. Also, our multiple model served as a plug-in model for the DNA. It can evaluate the DNA performance and using ensemble method for robust estimation. And also by using active learning, we can have less label required. Okay, that's all about my presentation. Thank you all. If you have any question, we can discuss later, or you can reach out to these 3 emails. Thank you.
Thank you. Thanks, Xiaowei.
Thank you. Yeah.
Yeah, I think we have a couple of minutes for questions. You want,
yeah,
or we can move it to the panel as you want.
Okay, if there are no questions, but I think right now we have a poster paper presented by Casper Osterheld and Vincent Konitzer, extracting money from causal decision theorists.
All right. Yeah. Hi, everyone. So that's me. So I guess I should share my screen now.
Please.
Okay. Okay. I hope you can see my screen and hear me.
Yep. We can see it, Casper.
Yes? Okay. So then I'll start. All right. So yeah, as mentioned, so yeah, I'm Casper Osterheld, and this is joint work with my PhD advisor Vincent Konitzer. So I'll start by giving some background by explaining Newcomb's problem, which is a decision problem that was introduced by that was introduced to the decision theoretic literature by Robert Nozick in 1969. So it's quite old by the standards of computer science, and it has been discussed passionately ever since. So here's how the problem goes. So some entity offers you 2 boxes, and they're labeled box A and box B. And box A simply contains $1,000, and box B contains either $1 million or nothing. And you can now choose whether to receive the contents of both boxes or only the content of box B. Okay, now the twist to this decision problem is that yesterday, the being, whoever sells offers you these boxes, filled box B if and only if it predicted that you or the agent would choose only box B and forgo the $1,000 in box A. Okay, so that's the decision problem. And now, what should you choose? Should you take 1 box or both boxes? And decision theorists have disagreed about this problem and developed various sort of lines of reasoning and thought about what kind of learning algorithms might converge to and stuff like that. And they've also given sort of general theories of rational choice that arrive at different recommendations in this problem. And I'll briefly describe causal decision theory, or CDT for short, which is the main theory that recommends 2-boxing in this problem. So CDT reasons that the agent cannot causally affect what is in box B. And so when CDT calculates the expected utilities for 1-boxing and 2-boxing, it uses the same unconditional probability that box B is full. So if you see my cursor, this probability is the same. So that the CDT sort of imagines that regardless of whether the agent 1 boxes or 2 boxes, the chances that box B is full is the same. But now, since taking 2 boxes gives you these extra $1,000 in box A, CDT always recommends that you should 2 box, so take the contents of both boxes. And others have argued that one should 1 box, and evidential decision theory is sort of the main theory that supports 1 boxing, but there's sort of other theories that have been proposed. In general, the justification for 1 boxing is that that is usually given is that if you 1 box, it is highly likely that the being predicted that you would 1 box, assuming that the being is sufficiently accurate, and therefore that box B is full. Okay, so in the paper, we discuss various kinds of scenarios in which CDT and other similar theories that recommend 2 boxing in Newcomb's problem voluntarily lose money. And we present these scenarios as arguments against these theories. And I here only give the sort of very simplest such scenario. So once again, a being offers 2 boxes, but this time each box costs some price, maybe $1. And each of the boxes contains $3 or nothing. And also, the agent can buy at most 1 of the 2 boxes. Like, you can't purchase both boxes. And also, we assume that you cannot randomize, and you can read the paper for extensions that drop this kind of annoying, inconvenient assumption. But for now, let's assume that the agent cannot randomize. So here are the 2 boxes again. And now in this case, this sort of prediction twist that is supposed to be somewhat analogous to Newcomb's problem is that yesterday the being filled each box it predicted you not to purchase. So for example, if the being predicts that you choose box 1, then box 1 will be empty and box 2 will contain $3. And again, we imagine that the being's predictions are very accurate. So for example, that it's right 75% of the time or something like that. Now, the first thing to notice about this problem is that buying a box seems like a bad idea. And I think the most straightforward way to come to this conclusion is to assume the perspective of the being that, or the person or whatever that offers these 2 boxes. And to sort of imagine that you're selling these boxes and there's some outside process that is sort of the buyer, but you imagine that this is just some thing that you can model and predict in the regular way, and it's in the environment, and it decides whether, or it arrives at a decision somehow of whether to buy 1 of the boxes or not. And then you would hope that this buyer would buy a box, because most of the time when they buy a box, you receive $1 and lose nothing, or you lose nothing you lose less than $1 in expectation. And in line with this, theories that 1 box in Newcomb's problem basically also recommend not buying a box in this problem. Okay, but now I'll argue that causal decision theory always recommends buying a box, and thus taking this loss. So to see why, let's look at the sum of these 2 causal expected utilities. So the sum of the causal expected utility of buying box 1 and the causal expected utility of buying box 2. And each can be rewritten as in this second line. So it's a probability that box 1 contains the $3 times $3 minus $1, and then the same for box 2. And of course, it's sort of hard to tell what these probabilities should be, where the money is. But and this is sort of a key idea, because of the way that the boxes are filled, these probabilities must sum up to at least 1, because at least 1 of the boxes contains money. And this means that this entire term is at least $1. And so we've now shown that the sum of these causal utilities is at least 1. This means that at least 1 of these 2 terms must be at least 1. So at least 1 of these causal expected utilities of buying a box must be at least one and therefore better than not buying any box. And so CDT recommends buying a box. And from that, we conclude that agents who abide by causal decision theory are vulnerable to these schemes in which they volunteer to worsen their situation or lose money. And because this seems undesirable, orthodox causal decision theory should be rejected. Thank you for listening.
Thank you, Kaspar. I think if people have questions, maybe we can save them for the debate. And now let's move on to the next speaker. Do we have Samantha Day?
Yes. Hi.
Hi, Samantha. So you're going to present safety augmentation in decision trees, right?
Yeah.
Okay. Go ahead.
So I hope you can see my screen.
Yes, we can see it now.
Okay. Thank you. Hi everyone. So we are with Pallab Dasgupta sir, supervisor, me, Sumanta De, and Briti Gongopadhyay with us. So we start with we take a decent tree as a beginning for AISafety things. So to experiment with AISafety, because these are old, these are tree-like structure, old, well-known, widely used model. So that people's in the industry with safety critical who use the safety critical things for who use machine learning models started using machine learning models for safety critical things. So they use this kind of interpretable models because these are easy to verify and suitable, thus make it suitable for safety critical domain. So these are kind the right hand side there is a typical recentry model which predicts whether a mushroom is edible or poisonous based on the cap color and cap shape. So first thing is that learning decentry is learning decentry is a of NP complete problem. So because finding an optimal decentry with minimum height is kind of combination, finding a combination of all those attributes. So so people actually find some alternative approach, use some alternative approach, greedy approach to find suboptimal decentry. So one such example is ID3 algorithm, which use entropy or information gain, to actually order the nodes or attributes. So we first start with why we require the safety augmentation in decentry, because there can be some noise or some missing data which may lead to the catastrophic or fatal decision. Like here we can see if we have this kind of mushroom data set which actually predicts poisonous and edible mushroom, then this is a figure, this is the decentry actually learned from this mushroom data set. Here we can see that we can see that the cap color with yellow and a cap color with yellow is edible and cap color with pink is poisonous. But suppose there's some known fact or domain knowledge. From domain knowledge we have some idea that cap shape, if the cap shape is like bell and gill color is like green, then the mushroom might be poisonous or mushroom is poisonous. But we can see this kind of safety features actually is contradicting with this decentry. So one way is how can we incorporate this kind of safety decision in safety actually domain knowledge or safety properties in the decentry. So one way is post-facto safety augmentation. So we are suggesting post-facto safety augmentation. It's because we actually first build the decentry in such a way that you first build the decision tree. After that, insert that, incorporate the safety assertion into the decision tree. So in that case, we can see that the decision tree can be modified in such a way. So the thing is that whenever the edges actually satisfying the decision, I mean the safety properties, then modify the safety assertion with the decision property. So here is one example that the cap color yellow and cap safe. Then actually there was the leaf node called edible. So we have to modify that thing. So we have to reinsert some safety properties there, that cap safe equal to pale and gill color is green, then poisonous. Rest of the other subtree, the newly incorporated subtree with the previously learned safety, previously learned leaf node value edible. So this actually, in this process, the main problem is that the decision tree become very complex or large. So we actually think about these things, and we want to apply. We want to use the benefits of this greedy algorithm to create the decision tree. So let the ID3 algorithm handle this kind of thing to create the decision tree. So we can have this small decision tree or suboptimal decision tree. So there can be two methods actually. One is to explicitly generate the support datasets of these safety properties, then actually use these safety properties to use the support dataset along with the input dataset, and then use the ID3 algorithm to create the decision tree. So the first thing is that here we can't use the decision node value based on the majority count, what sometimes we use to prune the unwanted lengthy decision choices. So another method, as we are only dealing with the count, so the count of the data items in the data set. So why we have to generate this? Why we have to generate this data set? We can count. The thing is that we can count based on that combination or value of values that each attribute has. So from these things, actually, we came to this idea that without generating the dataset, why we don't have to, if we use the implicit count from that support dataset. So here, just we have to change that thing, change the probability, how we are calculating the probability to calculate the entropy and thus the information gain. So this is the new formula where NIT is the new count for any type of class for any branch T. So for class I for branch after branch T. So that is the count with RI. The RI is the class count at branch from the input dataset from the input dataset, and SI is the count comes from the support dataset. So there can be things that some support datasets actually already present in the safety. Already present in the input dataset. So we actually taking union of these values. So this is the actually advantage, because advantage from that explicit dataset, that it's faster than the implicit datasets. It takes less memory, less time, because it's not generating those support datasets. So another advantage is from the with the post factor augmentation is that it's most of the time it generates smaller decision tree. So, and another thing is but it has some disadvantage as well, like it introduces some unnecessary biases. Like in nature, we might have we don't have we don't have this kind of I mean we might don't have this kind of mushroom at all. Like from the support data sets, actually we can find that there is if there can be two possible mushroom, actually possible type of mushroom is missing from the input data sets. Like bell type is white and bell cap shape is bell, cap shape color is white, gill color is green, and then from the support data set, from the support data set, we can say poisonous, as well as the cap shape is bell, cap color is yellow, and gill color is green. Then also support data actually safety property is telling that it can be poisonous. So this our missing this was our missing safety property. But the problem is there can be missing support data sets from the input data sets. So there can be problem that the yellow color yellow cap shape, I mean cap shape bell and cap color is yellow mushroom is not might not present in the nature. So this kind of biases, unnecessary biases, can introduce in this explicitly and implicitly dataset augmentation method. So another thing is that if we have multiple assertions, so then actually we find we actually propose three methods, like three scenarios or as well as three methods. So if the assertions, multiple assertions has the same consequent, so then just take the union of the support data sets of all the assertions and just use the same formula. But if we have the different the assertions have different consequence, so then we have to ensure that the assertions are disjoint. Otherwise, we have to I mean order that assertions, which assertions we need to take, or prioritize the assertions. Another thing is that if we have causal versus diagnostic assertion, so in our methods, actually we are using only the causal assertions. So we have to convert that assertions into causal diagnostic assertion into the causal assertion using the following rule. So these are our experimental results, all based on that datasets available in UCI machine learning repository. So we use the first table. Actually, we actually proposing some safety properties based on after seeing this safety the possible safety properties. Actually, we are not using any I mean the safety properties available. So we just created any possible safety properties that can be possible. And the second table actually using those safety properties, and we are showing that how actually the decision trees nodes and nodes matters after the post facto safety augmentation with our integrated safety augmentations. So we can see the post facto safety augmentation always if we combine with the original decision tree build and post facto safety augmentation runtime, then we can see that integrated safety augmentation is most of the time giving the same or less runtime in seconds. And another thing is the total node counts is always lesser than the post facto safety augmentation, less than or equal to, or always less than or equal to the post facto safety augmentation, which means it's actually giving the better decision tree. So the thing is that as in conclusion, we can say that in using any models in safety critical domain, we must have to safety augment into the learning functions. And in our results also, we shows that the augmenting the information gain metric actually yields better safety decision tree than the post facto safety augmentation. So thank you. That's all from my side.
Thank you. Thanks, Samantha. Are there any questions?
Maybe one. So how does this compare with respect to, say, CART algorithm?
Sorry.
Let me type it in everyone. So there's this algorithm for decision trees, and I'm wondering how does your work compare to that type of algorithm for training decision trees?
Okay, so can you just okay.
It's a C-A-R-T, Samantha.
CART.
Yeah. So actually, I haven't gone through that that algorithm. Yes, you pointed out that algorithm. I will go through. Thank you. Safeguard. Is it safeguard?
It's CART algorithm. I don't remember exactly what it stands for.
Oh,
Yeah, it's
CART
classification
algorithm.
and regression trees. It's Braids and Braidmans. It's a classic.
Yes, yes, yes. So the problem is that for all I mean, the simple CART algorithm actually doesn't. I mean, from it's give the results. It's produced the descent tree only from the. It's produced the descent tree only from the. I mean, the input data sets. But there can be what we are suggesting that there can be some, I mean, safety properties known to known from the expertise or the data set could can be noisy. So in that case, the descent tree can I mean descent tree can learn the functions which might contradict with that safety property. So we are actually proposing method, how can we incorporate those safety properties or safety assertion into the descent tree such that it's always give the safe result from the known safety properties. And how we are incorporating these things. So any known algorithm are not able to learn any safe descents as per my knowledge from that from the if the input data sets is it's not missing or input data set is noisy. That's the thing. So
all right, thank you.
Thank you.
Thanks.
Okay, let's move on to the next speaker. It's a poster paper presented by Snehasis Banerjee, Towards Safe and Reliable Robot Task Planning. Snehasis, are you ready? We can see your screen. Not anymore. Banerjee? Oh, he's back.
We cannot hear you, Snehasis. We can see your screen very well, but we cannot hear you. So some issue with the microphone.
Are you speaking?
I think his microphone is okay, but it's not working properly.
Okay. The screen looks fine. You just can't hear him.
Maybe you need to configure your microphone.
Yeah. Snehasis? Hello? I mean, oh, okay. I mean, we can see him. I can see him. But you're moving your lips, but we can't Hello.
Just try to configure your microphone in the left bottom side under configuration of the microphone. You can maybe change the settings of the microphone. So he's reconnecting. Yeah. He's back again.
Still, we can't hear you. Has it?
You can see his video. Oh, there was something.
Yeah. Right. You can change to built-in audio analog stereo or something like that. You have two options for the
Yes,
microphone.
maybe the other option. Let's try that.
It's the same.
Audio settings.
Audio.
No.
Maybe you can check whether you have another app capturing your mic. That's happens. If you are on Gather Town, maybe you can close it, because I had a similar problem before. That the Gather Town was using my mic at the same time that I was on Zoom.
Okay. Yeah, maybe. Okay. You'll try to rejoin. I guess we can move on to the next section, which is debate. While we wait for Shanasis to join.
Yeah, maybe we can open the discussion for the first three presentations. And if at any point Shanasis is able to speak, we can listen to him. Maybe we can just switch there. So I think it's Huáscar, you and me, that we should start with the panel.
Yes, because Cynthia is not available for the first session. She will be available for the second session. So yeah, we can start with the questions.
Yeah. So maybe I can start. Yeah, we have three very different papers, topics. So I'm going to start with the first one. I have to admit that I didn't understand so the final application of or the final setting. There's a deployment situation. There's a monitoring system. But to me, there's something that I would like to understand a little bit better. So you can have some kind of a calibration system where you know whether you're going to make you can have a calibrating system telling that the system is giving you correct probabilities or accurate probabilities. Here, it seems like it is more like a batch estimation where you have a sample of examples and you want to estimate the accuracy of that of examples. Is that right?
Yes, yes.
And why is it easier than just estimating the probabilities for each example and then aggregating them?
Yeah, we can't directly using the softmax probability, but we have the result. It's the MP result. What happened? Yeah. Hello?
Hello,
yeah, we were having some noise, but yeah, maybe you can repeat the last 10 seconds, please.
Actually, yeah, we have the baseline that's called MP. That's using the mean of softmax probability, but it doesn't give a good result because for the deep neural network, usually it's uncalibrated. So there will overconfidence about the probability. So you cannot directly using the probability. Actually, we have another work that is using this method to calibrate the probability. So yeah, so we are not saying that it's more faster or other things. It's just the performance is better than the directly using the softmax probability. If you are using softmax probability, even for the adversary one, they will have more than 0.9 value for the probability. So you cannot use that one. It's like the calibration process for the monitor part. Later on, we know that yeah, we have the post hoc calibration. So later on, we have another paper. We will talk about how to train a model from the probability to a new probability instead of just using the tensor schedule. Okay. Yeah.
Yeah, this reminds me a lot of the problem called quantification, where you want to know how many of your examples are predictive of a certain class. And in that case, it is much easier to solve the quantification problem for a batch of examples than trying to estimate for each example and then aggregate the results. That's typically worse than just calculating the number for the whole batch. Because you can exploit the distribution of that sample. So perhaps here it is much easier to say, okay, I have 100 examples of images, and I say, okay, I'm going to be accurate 92% of the times, than saying, for this particular instance, my probability of success is 87, for this other one is 95, and then I aggregate all of that and I get the 92. Maybe that approach is worse than just getting the 92 in the first place. So I think there's a very interesting connection with the problem of quantification, with something similar and some ways that go beyond doing calibration and then aggregating the results. So I think now I get it right. If you're addressing this kind of a batch problem rather than just instance-wise estimation.
Yeah, for instance-wise, yeah, it's directly the calibration one, I think. Now it's a batch one, yeah.
Mm. Yeah, so I don't know if you're familiar with the quantification literature, but I suggest you have a look. Maybe I think that your approach is different, especially, but maybe there's some connections.
Okay, thank you. Yeah, I think I will do more literature review about that part.
Thanks, Jose. Should we give Synehasis a chance to maybe present now?
Yeah.
Synehasis?
Yeah. Hello, can you hear me?
Yes, now we can hear
Yes.
you. Yeah.
Okay, so basically I joined from browser, so now it's working. When I joined from Zoom, it did not work anyway. So. Yes, so I think it is visible, right?
Yeah, now we can see your presentation.
So the work is about creating an idea that how should safety and reliability look like in case of robotic task planning. So reliability is generally determined by the probability of a task to circumvent failures, while safety is related to consequences of the failure. So in case of any service robot in a human occupied space, safety is the #1 priority. And including this workshop, there has been many works going on in this line. For example, the work by Amodei et al. Discusses 5 core research areas. So this paper deals with avoiding negative side effects, that is ensuring that the agent action meets safety constraints in some way, and also safe exploration, because any robot has to navigate, because navigation is a principal task of any robot. So how safely it can navigate. And obviously, this is even the morning started with this in our time, basically. And then there are other works that are ongoing in the recent, maybe last 3-4 years, 5 years, where machine learning models have been used. But the mixing of different models and bringing the flavor of task planning into this particular aspect has been missing a bit. So this is the first step to bring in those aspects in this particular landscape. So this starts with a simple high-level diagram, but starting with 2 simple use cases. So for example, for a wheel robot like this one that you can see, the stairs is a hazard for the robot. And also, if you look at a dark room, so a robot depends how well it can operate or execute a task. It depends on its perception and sensor as well. That is, what type of sensor it has, what is the reliability of that particular sensor, and also the environment. So in a dark room, there is always a problem with computer vision algorithms to decide what object is which. So this is a standard problem. So the safety of robot depends on multiple factors. These 2 are just examples. So the plan is that when we have an input perception, which can be like the audio, video, any sense data around the robot, and we also have knowledge. So this knowledge is something like, for in this picture, what are the objects here? So are they obstacles, or are they harmful, or is it okay to carry out my particular current task? So are they going to hamper them? So something like that. So some things can be already there in the database, and certain things has to be fetched from the web, because you cannot store everything and do like you cannot have a huge classification running at the same time. So it's always better to stitch it down into a particular location and then execute. And the idea is to mix planning and some sort of reasoning. There is some extension of whatever it is observing, and later mixing this RL part with this part. So as of now, what we have done a little bit is that we have implemented certain things in the planning part, but mixing of the RL part is still ongoing. So it's still on an experimental stage. Now, so these are the thought processes that how this can be done. That is, how can we bring in the parameter of safety as well as reliability here. So one way is to bring in the old aspect of PDDL, to extend it and use its existing ways in which you can define a metric and define reliability to each of the tasks and the subtask, and also safety, and then you create and optimize on the total reliability and total safety. Another option is to have safety priorities and vulnerability values. So for example, each of the objects that exist in the wall model, we can assign vulnerability score and as well as safety priority. And we can create a weighted goal that, okay, so for this task, this needs to be done. And another important thing is that there are multiple aspects. For example, when a robot is moving, in technological terms, we call it the world model. So it observes the world state. So even the world state has a reliability. The individual state, the state in which the current robot is, that also has a particular reliability. And once the robot moves from one task to another task, so that task transition, that also has reliability. For example, when you, for example, the task A is turn off the light, and then the task is move forward. But for a robot which does not have infrared camera, it will be very difficult. So that task transition reliability is not good. And similarly, task execution reliability. For example, the robot picks a heavy object which is more than its allowed physical weight. So, so in this regard, an interesting thing has been conceptually introduced is something called task reliability graph. So here you start from the top, and there can be multiple tasks, ways in which you reach a goal. And we define certain things like safe zone, risk zone, and failure zone. So failure zone is something that, for example, the robot reaches the stairs and it falls down. So there is no way it can recover without a manual help. Risk zone is that it has high chance of failure, but it can recover, backtrack and something. And safe zone is that it's fine for the robot senses the world that it's fine to do its task. And there can be reliable transitions, that is from one task to another task. So there can be reliable transitions. There can be transition with risks, depending on the particular perception observed. And there can be unreliable transitions. For example, picking up weight more than the weight of the robot. So if we look at this particular graph, so there can be case one, say, if safety is highest priority, then there is no path in this particular chart. There is no path to reach the goal. But if you reduce, like if the second is that sometimes you need to do some emergency work, and that is emergency do something. Maybe in a elderly care you need to reach to elderly people to support him or her in a quick time. So then you can avoid certain things in case of service robots. You don't need to, maybe you can enter the risk zone and do certain things. So there is a path, like task 1, then task 3, and then goal. So this is a path, but there is this rate unreliable transition is also there. And there is another path that is more or less okay. So this, if time and safety are relaxed priority, then this last part is good. So these are the options that in which it can propagate based on the goals it is and the safety requirements of the particular use case and the situation. And finally, this is sort of a way, an approach, or what should I say, attempt to put this in an algorithm format. So perception is the input, actuation is the left, right, whatever way. In case of drone, it will be something else. Knowledge, as I mentioned, so certain things won't be classified. You need to have access to external knowledge. The software is just for this, helping you out with the algorithm. And current state is the current world model state of the robot. And at each level, it should generate a sub-plan. So if, for example, it will always monitor and detect state changes. So if change detected in the world, then it should evaluate the perception. This part, reinforcement learned model, we are still configuring, but other things we have more or less tried to implement. So we can take help of the task reliability graph and look forward that which one is the best path. And we can also do a voting between these two. That is, what is the best path between RL and knowledge-based, graph-based detection. And also we need to update our graph accordingly. And there were earlier, if you remember, there were some weights, metric weights that we can also update. And finally, we either reach the goal or we replan based on your current perception and the world state and where you are in the task reliability graph. So this is in short what the work was about, the preliminary work that's going on. So I will open up to questions.
Thank you.
Yeah. Yeah.
Okay. I have just a question. I think
it has a certificate. Okay. Yep. I think that's where.
Okay.
It's coming from.
Okay, I have a question to the last speaker, Hernández. You mentioned that you plan to use PDDL for your approach. Is this some alternative you are exploring, or something that you are really using? So my question is, if you are using PDDL, how you are integrating safety aspects and the PDDL specification?
Right. So as I showed in the slides, so there is something called metric in PDDL. So as you know, that PDDL is just like a network, and it's an optimization problem. So there is already a keyword called metric, and in the metric, in each of the task transitions, you can mention that what is the reliability and safety of this, and how do you get to that? So one way to get to that is that depending on the sensors that you attach to a robot, there are some existing work in which you can run some sensor models. That is, in this situation, how well the sensor behaves, and also doing a lots of training on a particular environment, whether it's a habitat environment or a Gibson environment. So there are some robotic environments in which you can simulate the robots go around the world in a room or outdoor, and then get a feedback that which particular tasks are getting some problems and where some collisions and other things are happening. So accordingly, you can update and have a one-to-one mapping that this task, this is the reliability, this wall state, this is the reliability and safety, this task transition, task 1 to task 2, these are the reliability, and so after running the simulations, you get those values, both from the simulation as well as the existing work. How you can model the sensor reliability, like perception, any sensor that have to attach to the robot. So those two can be combined, and using a metric like parameter, and assigning each of these tasks and transitions, you can then by default the PDDL will give you a goal just by attaching this. But there are some limitations. That's why we want to combine many approaches together.
Okay, thanks. I had another question to Samantha from the decision trees presentation. It's not fully clear for me what kind of real examples you can apply your approach, because it was not so clear the kind of safety constraints or properties you can express with this approach. Have you explored what kind of real life examples you can use, for instance, in autonomous vehicles, if you want to use it in I don't know, in decisions and decision making, something that you could use it? What kind of constraints or problems or things you need to take into account to use it? These kind of real examples.
Okay, so hello. So, and we thought of these things. So we are already we actually wanted to apply in medical data sets. So like what we thought that if we have kind of some patients who is allergic to sulfur or any medicines from sulfur kind of or any kind of medicine. So before in our so in a emergency, if we have any medicine recommender system, so which already are in using in some hospitals and so on. So in those cases, actually, if we have like as we mentioned, National Healthcare NHS in UK actually use such kind of tabular data, tabular form of these things. So they actually recommend some activities and activities or plan which is manually created. So if we created those things from the from any input data sets, like previously doctor's prescriptions or these kind of things. So one things what we to verify these things, actually we have to go through, we have to create some safety assertions, like whether checking whether any medicines actually prescribed patients without checking whether he is allergic to that medicines or not. So these kind of things, this kind of already work is there. The problem is that if we incorporate these safety properties in this this entry, what we learn from the prescriptions, previous prescriptions, so then it will be easier for actually much more easier to predict. I mean, to recommend the medicines or to a patient, and to check whether what kind of diagnostic measure we have to take, because all these things actually are if the safety properties are created by the domain experts, then we can guarantee that he has some ideas about these things. So we can leverage both kind of, I mean, from the both world, which actually we are learning from the previous prescriptions, as well as we are actually to give the better results, as well as we are actually concerned, I mean, considering the safety properties from the domain experts. So we are combining both, we are actually giving some way to combining both decisions from both world, and give the safe and the best results to the for the patients, for the medicine recommender system or anything else. So we don't able to provide those kind of data sets results, because which actually those data sets are not publicly available that much. So that's it. Actually, we thought of that thing. So this kind of real value, real examples, but we don't have any such kind of thing.
Okay, thank you. Is there
I have another question for Samantha. I was a little bit surprised by this this combination of decision trees with constraints, because I expected these to have been addressed many years ago. Especially, I was just during your presentation, I was Googling about decision trees with constraints, rural learning with constraints, and I found some of the old papers about constraints in the number of the depth of the tree, or some other constraints in terms of monotonicity of the rules. But I didn't find, maybe I haven't found, I haven't looked enough, but I haven't found a paper about just having constraints. But to me, it is very simple just to include a pre-processing step where you have your constraints. You just apply your constraints and you say, okay, this is this and this is this. You have to predict that. Otherwise, you apply the decision tree. So I don't really see the problem. I wasn't able to understand why you have to introduce these constraints when you learn the tree. Can you explain a little bit further about this?
Sorry, I actually missed the last part, what you told.
So the thing is that you have some assertions. You can just pre-process the assertions. If this is A and this other attribute is B, I have to predict whatever. Do that. And if your case is not any of these assertions, then you run the decision tree as a by default thing. But you can just take the assertions first, and you can learn your decision tree as usual. Or in another case, you can just add some generated examples using these assertions when you generate the tree. So there are many options where you don't really need to modify the learning algorithm. So my question is, what am I missing here?
Okay, so one thing is that the assertions, actually, if we take such one small example, like from the assertions, we can say that for a medical recommender system, like if the patient is allergic to sulfur, then recommend these medicines. So if we take these assertions only thing, so each time we have to, we have to predict, we have to give the allergic reaction, prescribe the patients whether to check whether he is allergic to such medicines or not. But if we take assertions that actually this and after the medical recommender system predict that medicines, then that medicines only, then we can say it's actually valuable to doing that test. So another thing is that if I understand correctly, why we not, solely applying the assertions results instead of the dysentery result. So the thing is that we actually combining both the world of from like what I previously said, that learning algorithm to leverage the best thing for the best possible thing for that for any recommender system and classification system. And another thing is we are using that safety assertions to give the known safety assertion into the recommender system. We are changing that thing, the recommender system, such a way that it always gives the safety, known safe results. So this kind of thing. Another thing is that we are not we are merging these two things because there can be situations. We have to have two different methods. One is that if we don't merge it, like one is for recommending that task, and another for recommending from the learning systems. And another thing is that we have to have some kind of rule engine to generate the output from the rules. Then we have to combine whether we have to decide if we have to decide which value is to take based on the safety safety assertions. So these things actually we are merging into one into the same learning system, such that we don't require the two special separate things like rule engine to output from the safety properties, and the thing is that from the learn one.
Okay, thank you.
Is that what you are asking?
Yeah, well, I'm not sure, but I think that maybe we can leave it here. Maybe we can continue later. I have a question for Casper, and I'm sorry if at some point during his presentation I wasn't sure it was yesterday, today, or tomorrow because of the time here, which is about almost 3 a.m. Here in Europe. But this reminds me, of course, some of the, in terms of, I wasn't aware of this new Combs problem, but there are some other related problems in decision theory related to safety and related to metacognition. So such as, what's the next action you are most sure of? Or do the action, if you just build an agent where you have to do the next action you are most confident of, then you end up doing something very stupid as an agent. My question is, how much of this is related to basically past and future and all of these temporal things, and how much is related to an agent that in this scenario, in this new Combs problem, you have an agent that has complete true knowledge about something, which is perhaps unrealistic. And that might lead to paradoxes.
Okay, so I'm not sure I understand the question exactly. So I mean, there are definitely some connections to like temporal stuff. I mean, causality is like, I mean, people connect causality and time a lot, I guess, in philosophy. I didn't. Can you say again this part?
Well, the thing is that you have a system, and your paradox, there's an agent that knows something about the future. Okay, you can call it. You can just address that. You try to understand this and calculate that in terms of causality, but originally that's time, and you have an agent that knows something that is going to happen, and you know that's true, and that is the paradox appears. So my question is, how much of it comes because of time, or how much of it comes because of having complete certainty about something, omniscience? It is because of the two things, or it is just because one of the two? That's my idea.
Okay, so it's the question. So it's the kind of scenario that you're thinking of. It's like something like an agent knows that. Let's try to come up with. So one example that people are something like, if you know that you won't drown tomorrow, then there's no point in learning to swim, and then you don't learn to swim, and then you drown after all, or something like that. Is it something like this where, like, you know something? So I'm not exactly sure what you mean. It's like knowing that something is going to happen.
My question is, for an agent, a real agent in a safety situation, what's some of these results in decision theory are very important when you design a system, and you don't want the system to end up in some kind of a strange loops or something like that. The typical example, if you just create, not a reinforcement learning agent, but an agent and you just choose the next action, the action you're most sure of, there's some results that you can see that the agent degenerates in a way. So that and so I think that these theoretical results are very useful sometimes to understand that in some situations. I was just a little bit trying to understand one situation where an agent could behave unsafely, and you can apply some of it. It's more like, oh, this causal decision theory works or doesn't work, and you want to use it for another problem, be aware. So a little bit more about this kind of context for safety, or for a practical case.
Actually, Jose, no, I'm sorry. Kaspar, go ahead.
Okay, I said something, but please say your thing afterwards as well. So yeah, I think these kind of things, like where you, like, for example, if you know that you're going to take a particular action, then like you get various paradoxes where it becomes very tricky to condition on all your, like, to think, like, if I know that I'm going to do X, and it's hard to ask, like, well, but what would happen if I did Y? And I think that's, and then you get these strange things where it's like the conditioning on something false, everything follows and stuff like that. And that's, I think, maybe somewhat related. And I think it also like points to an interesting sort of gap in these like evidential decision theory and causal decision theories. So often it's they kind of assume that you kind of get these conditional probabilities from somewhere, but there are these kind of paradoxes, and you have to think about how to get around them. And then as for like how, I don't know, thinking about like safety scenarios, like a sort of safety case where this kind of stuff might be relevant. So I think one thing that one could think about is like, I don't know, you build some agents and you use it uses some like causal inference mechanism, and it builds like these causal graphs. Like you might know that work by Judea Pearl on the causal graphs and causal on inference on causal graphs, and then it uses some approximation perhaps to this. So it's, Pearl calls it the do calculus, so it's like intervention calculus for deciding based on causal graphs. And that's essentially causal decision theory. And Pearl also talks about causal decision theory and so on. And I think like you could imagine like deploying such a system. And in many cases, I think this would work perfectly fine. I think if there's no predictor in the, like no strange thing in the environment that tries to trick your agents to do silly stuff, then I think causal decision theory works fine, and it's like building a causal graph and doing the do calculus or whatever to calculate expected utilities is fine. But then what this paper, like you could interpret this paper as sort of pointing at, like, if you release the system to the wild, then it might run into a situation where it can be tricked into doing like giving away resources, or like voluntarily giving up utility for nothing, basically, which I think fits into like a lot of these kind of AI, like these sort of robustness AI safety considerations, where you think about like, okay, so this system might work in your lab or whatever, but then if you release it to interact with adversaries and with like things in the real world that you might not be able to test effectively in your training environment, then you might want the system to have some good properties still, and causal decision theory lacks, for example, the immunity to these money extraction schemes. I hope that says at least something that has something to do with what you were interested
Casper, actually, I thought that your presentation covered more like a security problem, which has, of course, safety implications, right? I thought that you have two agents, right, who could act adversarially. And I mean, I think there are many security applications to this sort of conjecture that you put together. And have you thought about maybe mapping this to a security problem, where the adversary, exploits this vulnerability, right? And then maybe some, I don't know, side channel attack or something like that.
Yeah, I mean, I've at least thought a bit about, so I mean, I do a lot of sort of game theoretical work, and there's this sort of like this kind of mapping between like these decision theoretic concepts and game theory. And there, of course, you get, I mean, you can kind of think of this adversarial offer that I described as playing like rock, paper, scissors against someone who knows what you're going to do.
Yep.
I think I haven't thought about something super practical, but yeah, I agree that like, especially like the specific scenario that I described, like it's a security kind of, like you can think of it as a kind of security scenario. Yeah.
And I think that's kind of what I liked about your presentation, which kind of broadens a bit the scope of this workshop, because I think, safety, I mean, security has safety, strong connections to safety, right?
Yeah, I agree. Thanks.
Okay. I don't know if is there any other question? Otherwise, I think
I had one last question for Snehasis, where I think he's relying on a exhaustive description, right, of all the states, which is fairly abstract. I think it's I mean, it's good for theory, but I'm not sure it's very practical. I mean, how do you deal with a more realistic system, right, that has a very large number of states, and the graphs would become very, very big, right? And in many cases you cannot really enumerate all the states. So how does this approach, extend? Because I mean, it sounds like this applies well to a structured environment, where you know exactly where things are going to be, and you can describe safety in very concrete terms.
Yeah, so our target has been service robot in a office setting as an initial target. So in the office or indoors, more or less the layouts and the objects, what we expect are more or less not infinite, or we can have an idea. So if we put it in the test for the real world outside, that is for the outside, maybe in the streets and other things, then it will become, then we using this, it will be difficult, then we have to use heuristic and something else. But for the indoor environment, whatever our current target of service robot is, indoor spaces, hotels and office spaces. So because the number of tasks and the number of objects that it will encounter is limited, and it is more or less tractable in the real time for this use case. Whereas if we follow an RL based things, we also tried that out, but we could not encode the semantics into that. So there has been a bottleneck in the RL based approaches. So we thought that best way to so we are having two threads in our working group. So one group is trying the RL approach, another group is trying the PDDL and the task graph approach, and later we see what are the bottlenecks and what are the advantages, and we might combine together both these things, and based on situation we can have a voting that which particular decision to select. So that will be our future work, and probably in next workshop I think we will be able to present it if we get accepted.
Thank you.
Okay, so if there is no more questions, Mauricio, I think we need to go to the break.
Okay, yes.
We plan 30 minutes for the break, but I think we need to shorten this. Since it's virtual, I don't think it's a problem. So I propose you to start at 2:15, so it means 5 minutes later than planned.
Yeah, okay.
So we will
10
have
minutes.
only 10 minutes break, sorry.
Yeah.
Do not
Quarter after the hour.
Yeah.
Okay.
So you can keep connected, or you can come back later. Just a reminder about the vote for the Best Paper Award. You have here the link and the code. So I will let you. I will share my screen for anyone that wants to see the numbers. Okay. So see you in 10 minutes.
Filed and 5 granted. In 2020, Natalie received the IBM Master Inventor distinction. She has published more than 20 papers in peer-reviewed conferences and journals, receiving 3 Best Paper awards. Natalie received her PhD degree from the University of Pittsburgh in 2016. I'd like to welcome Natalie to the stage for our next invited talk.
All right, thank you for the introduction, Richard. So today I'm very excited to talk to you about one of the projects that I have been working, which is federated learning. And this really is an exciting field, and I think it's going to have a lot of, or I know there are a lot of security and privacy challenges that I'd like to discuss with you today. And so just to start, I want to say, why do we actually care about this? And in reality, when we are going to train a machine learning model, getting quality training data, it's paramount. But that's not always easy. In fact, what we can see is that there are a lot of privacy concerns because the data itself belongs to individuals, or because of regulations like GDPR, HIPAA, and the California Consumer Privacy Act, among many others, that inhibit really the transmission to a central place of this data. Additionally, we see that companies have also stored their data in multiple cloud providers or data warehouses, and in some cases, even in different countries. And that, again, it's very difficult to manage and to transmit to a central place. Another concern that we see in companies is liability. So more and more with these new legislations, we see that companies are getting fined. And you can see here, I have posted one article where British Airlines got a substantial fine for violating one of these policies, this legislation. There are other reasons for which we have concerns and difficulty having training machine learning models. One of them, for instance, is the exposure of trade secrets. In the manufacturing world, for instance, we have machines that are deployed in different factories, but the factories, even though would benefit highly of having this predictive and having sent the different parts of these machines on time, they are not likely to share information with the companies that actually maintain those machines. Why? Because it may leak their trade secrets. And finally, we also have the case of consortiums. So imagine a real use case, it's banks. It is difficult to train fraud detection and anti-money laundering models, because each of the banks has only a piece of the data and they don't have enough information, but they could work together to construct one single model, and that would help drastically improve their machine learning model. The question is, how can we actually make sure that we can build machine learning models without transmitting the data to a single place? And luckily, federated learning has arose as one of the fields that allow us to do just that. So the data remains with the right person, with the right owner, but we still are able to collaborate to train a single machine learning model. This is not science fiction. IBM has a product that we released last year. And also, if you own one of these beautiful cell phones, you are more likely already part of federated learning. It was introduced by Google in 2016. So it's a little bit new, but not too super new. It's already using multiple production systems. And how does this whole magic actually happen? Here I have the different parties, and each party holds its own data set. None of them really want to share with anyone. So we introduce an aggregator that it's going to orchestrate that learning process. The first thing that happens is that the aggregator sends a query, and we can train a bunch of different types of machine learning models, going from neural network, decision trees. We have XGBoost, SVM, and you name it. It's possible to transform these algorithms. So the aggregator sends that query requesting, for instance, in an SGD system for gradients. Each of the parties is going to take that query and answer it based on their database and send a reply back to the aggregator. That reply, when everything is received by the aggregator, it's used to find a single machine learning model that it's going to be shared by all the different parties. And this may take several rounds, so it's an iterative process until we arrive at right accuracy. So what happens next? Just want to highlight, you can see here, no data was shared whatsoever explicitly. That's great. So this is very good. If we have a fully trusted system, we could live with this. But what can go wrong? So I'm a security person, and I always ask myself, what can go wrong? And in these circumstances, today I'm going to focus on two different aspects of things that may not work. The first one are the inference prevention, the inference attacks to the private data. And the second one are the model manipulations. So now I'm going to take each of those two threads and explain what they are and give you a hint of the research that we are doing and that I'm doing currently and with my team. The first one is inference of private data. So what do I mean with this? There are two attack surfaces here. The first one is the final model or intermediate model. And here it has been demonstrated that we have membership inference attacks. So if an adversary has access to that model and it's capable of querying that data, that model, it can actually extract some of the data points that we're using for training. And that's clearly an issue for privacy. In particular, and imagine that this data set that we see here, the adversary knows was collected from patients that have AIDS. Just discovering this data point, for instance, would be a violation of the privacy of that user. So that's definitely an issue. The second attack surface that we see in this process with respect to inference is this reply. So remember that I said these replies are, for instance, the weights or the gradients and so forth. And it's been shown that if you inspect these replies, you're going to be able to actually get some valuable information of what data was stored here. So here, for example, this is a gradient of a number 0, and it's clear it's at 0. Now, it's not necessarily only related to images. If we are training a classifier using a bag of words and we see a gradient that it's 1 for a particular word, then we already know that that word was in that data set. And that may be problematic and leading to inferences. For instance, if a company is going to buy another one or something like that, then it's a privacy violation. And there has been more additional attacks. For instance, it's been demonstrated that you can determine whether somebody was wearing glasses in a picture of a particular class. So it's kind of worrisome. So what do we do about this? So one solution is to use local differential privacy, where you have a query and each of the parties is going to take that query and add some noise according to differential privacy. And with that, the final model and the intermediate reply, it's going to be protected from any potential privacy violation. The issue that we have here is that we are building machine learning models because we want to use them in critical applications, and pretty much we want these models to be really accurate. But if we do this, the problem we are facing is that accuracy drops drastically. So we need to do much better than this. So we propose one solution for this that turned out to be very, very good, which requires combining multi-party computation with differential privacy. So for those that are not very familiar with multi-party computation, it's a technique that allows you to take an encrypted text and aggregate it. In this case, for instance, each of the different parties are going to encrypt their reply, their noisy reply, and send it back to the aggregator. And the aggregator takes that encrypted replies, that set of encrypted text, and aggregate them without getting to know each of the individual plain text from the parties. Because the aggregator does not need to know the individual replies of each of the parties, we are able to reduce the amount of noise that we inject during the training process by a factor of n, which is fantastic because we want better models at the end of the day. All the details in this paper. And multi-party computation and differential privacy is really a match made in heaven. Because we can reduce substantially the noise. And just to give you a flavor of what happens. So here in red was the baseline. If you inject the noise at each of the parties individually, and we have in the y-axis the F-score. You can see that the F1 score drops drastically if you use that type of system. But if you use our approach, it it maintains in the right amount of F1 score. Of course, if you didn't add any noise, you would have this type of accuracy, but nothing is for free, right? So we need to pay for privacy, and our solution allows us to have exactly a good balance between privacy and accuracy. Now, that's all good. We have found a way to reduce the amount of noise, but can we actually reduce the training time? So every time we encrypt, we augment the training time, and if we have a large model, then that becomes really a problem. And the other problem that we have when we use encryption techniques is that if some of the parties leave or just drop because of connectivity in some of the rounds, then we probably need to rekey the entire system, and that slows down the system furthermore. And the question is, what crypto system should we use? And it turns out that there are different secure multi-party computations techniques out there that may apply to different threat models. So for instance, here, this is one that it's very used by our community. This is Palier. And here the idea is you don't trust the aggregator. So the aggregator never gets to see anything about your model. The other possibility is if you don't trust some of the participants for some reason, because you think they may collude and they may try to get your data, then you can use something different like threshold Palier. You can see the number of iterations that we have throughout the process. It changes as the threat model and the crypto system model, it's varied. So we came up with another approach which requires you to partially trust the aggregator. And on average, we were able to reduce the training time by 68% and the data transfer by an amount of 92%. So this is a paper, and just to give you a hint of what we did, we took functional encryption as a way to model the problem, and we took advantage of the fact that fusion algorithms, the ones that take all the replies from the different parties, use inner product. So we can split these into the private part, these are the replies, and the weights. This comes encrypted from the parties, and this part is really coming from the aggregator. With that, we can compute all these without decrypting at any point this X sub I. So that's kind of a hint of how we do it. Now, what are the challenges here? There's a lot of ongoing efforts to make sure that we can use secure multi-party mechanisms without incurring into too much overhead or rekeying. And then also from the differential privacy perspective, we have two big issues in my opinion. The first one is epsilon. So this beautiful epsilon that I have here, nobody really knows how much we need in order to prevent inference attacks. And it kind of depends on the type of data set as well. So it would be nice if we can have some intuition into how to set up this. Also, every time you hit the data, it's not like you can keep hitting the data, because then you spend all your epsilon in things that you didn't want to. So that definitely is one of the research directions that I see out there. The other one is convergence. So as we add noise, it becomes more and more difficult for the model to converge. And it's been shown, and I have found that it becomes an issue to actually make the model converge. And if that doesn't happen, then the entire process doesn't work. So we definitely would benefit as a community of better ways to have convergence for machine learning models trained with differential privacy. The second threat that I want to talk about is model manipulation. And this basically happens when the parties decide to send something that's wrong. It may be that it's not one party, it may be parties colluding. It may be parties colluding with the aggregator. So there's a lot of new, since we have many more entities in the system, we also have many more things to worry about here. And an example of something that may go wrong is backdoor attacks. So probably everybody here in this community knows about it, but I'm just going to mention briefly what that is. We have a sample and the adversary adds a trigger like this little post-it note here, and then mislabel that sample. At the end of the day, every time this little trigger is part of the picture, the classifier is going to learn to identify it as a speed limit. But for all other types of stop signs, the classifier doesn't make the mistakes. So does that work for, can we launch as an adversary this type of attack? And the answer is yes. It is very simple, same thing as you would do in a centralized setting, only that from the defender, you don't have the data. So it's a little bit more difficult to actually try this out. But it doesn't stop there. There's been in the literature these other types of attacks that, for instance, distribute the trigger among multiple colluding participants. And when that happens, you don't really have a single participant sending the trigger, and that makes it more difficult to detect as well. Other types of attacks that we have are Byzantine attacks. And you can see here, basically, different nodes may try to send malicious updates just so that the model doesn't converge at all. So the difference is that while the other ones were related to the samples, these ones are actually manipulating the model updates. Sorry, my phone is ringing. The aggregator. So the aggregator is in most cases the one that it's assumed to be the defender in the literature, which from the standpoint of view of companies like IBM makes a lot of sense, because we want to make sure that whatever we're training with our services and products is resilient against participants that are manipulating their system. The issue though is that we no longer have the luxury of information that we used to have in a centralized setting, because we don't know what data each of the parties has. So, and we cannot really access that data. That's the whole premises of federated learning, is your data is your data, and I don't know it, I cannot have it. So it may happen that we have IID data, so all the parties have around the same data, and the model updates are therefore going to be similar. But in reality, and one of the reasons we actually may engage in federated learning is because we want to have a little bit of different set of data, so that we can learn things that we could not learn before because we didn't have access to the training data. So we don't know what case it is. And it may be good, it may be bad. And so applying robust statistics on those model updates itself, it's not going to solve the problem. It's a little bit more complex than in centralized setting. Also, the number of data points per party may differ, and the quality of the data is unknown. So we can no longer inspect or do any of those things that we normally do when we have a centralized use case. So the defender doesn't have access to the data, and it's a whole different game from that perspective. And yeah, so that's I think the main issue, and one of the reasons it's a very, very active research area at this point. Now, it is difficult to know. We have been studying the problem, and we have an upcoming paper called Course of Redemption, how data heterogeneity affects the robustness of federating, that's going to appear in AAAI. And there, what we analyze are potential, first, how does the entire set of attacks affect the model based on the situation of whether we have no IID or not, and potential solutions for this. So, for instance, when the adversary launches the attack during the training process, has a huge effect, and it's potentially something that we can use as a defense to these types of attacks. Okay, so I have talked so far about two different types of attacks. one type of attack was about privacy, and I don't want my data to be inferred by anyone. And then there's the other one where we have malicious entities sending data that's not okay. So what if I want to protect against both? Currently, there's really no good way to go about this. So there's this dichotomy that we need to solve. And I think that's one of the big challenges in this area, because we want to identify malicious entities, but at the same time, we want the privacy. So that makes it really a difficult problem. Besides the always the same issue that the defender comes with defense, and then the attacker uses that defense, adapts to that defense. So that's also another issue that also we face in standard AI security. And I would like to also mention that we have IBM Federated Learning. This is a library for experimental use that you can try it out if you're interested in doing some research in this area. We have this open source library. It's not open source, sorry. It's for the experimental use, but for commercial use, we also have a product that launched last year. It's in part of IBM Watson Machine Learning. And this library that I'm inviting you to use for research has different types of supported models. So you can train XGBoost, neural networks, logistic regression, SVMs, K-means, reinforcement learning. And we support a bunch of different standard and popular machine learning models, as you see here. How does it work? It is very simple. So basically you specify your neural network. In this example, this is a tiny one, Kira's model, so that it would fit my slide. And then you select your components using a YAML, all the configurations, all the fusion algorithms and type of model that you want to train, and start your aggregators and parties. And at the end of the day, you get your federated learning model trained for you. So hopefully this is quite simple. You don't need to, with respect to other available techniques, libraries out there, you don't really need to learn anything new. You can use your loved libraries. We also have a bunch of advanced fusion algorithms, which is something that I want to mention, because I see most of the research out there going to this type of algorithm, which is federated average. That one just basically takes all the model replies and average based on the number of samples that each of the parties had. But we have many more algorithms out there that could be interesting to use for different experiments. And we continuously are working to design more. My team in particular, we focus a lot on AI security and privacy. So that's one of the things that we're currently doing. And I want to just mention again, try it out. If you like it, please star us. And if you have any interesting problem that you'd like to discuss related to federated learning or any questions, please let me know. Thank you.
Awesome. Thank you so much, Natalie. Does anybody have any questions for Natalie?
Looks like super clear.
Yeah, I think everybody got it. I have a question. So with that tension between privacy and trying to determine if the provider of those gradients is pulling a fast one on you, do you think that's something that might ever be solved, or is there just too much tension there?
I think it's possible to solve it. We haven't done it yet, but I think we can make it happen. Yes, I think that's something that's going to be solved, because you don't need to know exactly what's going on. You need to have some hints about the distribution and other information. So I think if we consider that it may be possible to actually detect when people are deviating from what they should.
So I can imagine that you can detect inconsistencies in what they're saying like that. But if they're just fabricating an entirely new data set and then giving you answers about that, I would imagine that would be very difficult to detect.
Yes, you're right. Some of these attacks, however, what they do is they check this when, let me go back to this slide. Perhaps it's going to be easier. The attacks, most of the time, what they do is basically, they take the replies, the query, and as part of the query, usually the aggregator includes something like the current weights. So the attacker would use those current weights of the neural network, for instance, to identify what would be the best way to attack. For some of the attacks, for Factor it's slightly different, but for some of the attacks, that's what happens. And so they would adapt their reply based on that query that they got. If we want to deter those types of attacks, then we could potentially ensure that each of the parties would need to provide some information initially and kind of like a commitment to later on verify. But yeah, I think overall it's a difficult problem, and it all depends on also the type of crypto system that you select for protecting your private information.
I see.
Natalie, go ahead, Richard.
Oh no, please go ahead.
Yeah, thanks for that excellent talk. My question is, I mean, what markets are you addressing with these technologies? So who has, I mean, what market is pulling the most?
Different markets. So that example about the maintenance, predictive maintenance, that's actually a real use case because they want to make sure they send the right amount of replacement parts to the factory. But the factory, even though you would benefit from that predictive model, they are not willing to share the raw data because they feel they may lose competitive advantage. So that's an existing use case. The other existing use case is healthcare. In those settings, it's very, very difficult to actually send the data to a central place. And even, for instance, we have a use case where there's the same company owns the data sets, but they cannot jointly put it in a different place. So connecting those data sets for image processing, it's something that they are using the framework for. The bank use case, that's something also that we're pursuing. We participated in a hackathon of an UK bank, so it's still like from the it's that one it's still not in production, but I think it's something that will go on, will happen. So there's use cases in several, IoT also.
Okay, thank you. So is IBM always thinking about playing the role of aggregator, or what's kind of your take? So what segment of that market is IBM trying to target?
So right now we have two products. One is the aggregator as a service, so you can have it as in the cloud. And the other one is a private cloud. So basically we provide you with the code and the product so that you can deploy it in your private cloud and you run it yourself. So at the end of the day, IBM just provides the code, but you run it yourself as an aggregator.
Yeah. I think that's a model that some people would be more interested in, especially, in the defense and security industry. I think they want to, they have their own enclaves and their own, cloud.
Yes, highly regulated industries oftentimes don't go to public cloud. Yeah. So yes, I totally agree with that.
Thank you.
Okay, awesome. Well, thank you so much, Natalie.
Thank you.
And with that, we will go on to Rachel Friedman's talk.
Shall I go ahead and share my screen?
Please, yes. She's presenting on classifying choice set misspecification in reward inference. One of the candidates, by the way, for best paper.
All right, can you see the slide there?
Yep.
Great. In that case, I'll get started. Hey everyone, my name is Rachel Friedman, and here I'm presenting work in reward inference with Rohin Shah and Professor Ankur Dragan at the Center for Human Compatible AI at UC Berkeley. The goal with this is to improve a generalized form of value learning called reward rational implicit choice. I'll have the citation for that paper at the end of the talk, which can then reduce safety problems from objective misspecification. This talk is going to be in 3 parts, and then I will save some time for questions at the end. First, I'm going to describe what I mean by choice set misspecification, give an intuition for how it could arrive in practice, and discuss our work in evaluating and classifying different types of misspecification that correspond to different types of error in inference and in performance of reinforcement learning agents. I'll start with choice set misspecification. A common framework for reward inference is essentially Bayesian updating based on feedback. So the AI agent starts with some prior distribution over possible parameters for the human reward model. The human gives some kind of feedback, and then the AI updates its belief over reward models based on this new evidence. A really commonly used example is pairwise comparisons. In this specific case, the human can choose between 2 trajectories through a grid world, the orange trajectory and the purple one. These 2 trajectories are the ones in the top figure. The human chooses one of these trajectories. In this case, they choose the orange one, so that's the only one in the lower figure. The robot then updates its belief over the human's reward function based on the fact that the human prefers the orange over the purple trajectory. So in this case, the AI might assume that whatever that purple color is representing is bad and should be avoided because the human chose the longer trajectory that completely avoids the purple. We call the set of feedback choices that the human can choose amongst their choice set. That's the multiple trajectories that you see here. The trajectory that they actually choose, we call their feedback, which is the highlighted trajectory. In the case of pairwise comparisons, like I just showed you, the choice set is explicit because we know all of the trajectories that the human was choosing between. However, it doesn't necessarily have to be that way. For example, another familiar example of reward inference is learning from demonstrations or inverse reinforcement learning. This time, the human's choice set is implicit. So in IRL, the human is choosing between the set of all possible trajectories that they could demonstrate, but they're not going to literally enumerate all of these. So the AI has to be able to infer what these might be. Most other commonly used reward inference modalities can also be represented in this framework. The human has a choice set, they choose one element of their choice set as feedback, and then the AI updates on the fact that the human preferred that option to all others in order to infer what the human's values are. Sometimes the choice set is explicit, and sometimes the choice set is implicit, like in IRL. But when the choice set is implicit, this leaves the system open to a particularly subtle type of human model misspecification related to counterfactual reasoning. If the AI incorrectly models the human's implicit choice set, then it will have false beliefs about what the human could have done, which can actually lead to serious problems in value learning. So just to be clear, the AI sees the piece of feedback that the human gives, so the AI knows that that piece of feedback was in the human's choice set. But the AI could be wrong about what other pieces of feedback the human could have given. And in that case, I call that choice set misspecification. So to make this a little more clear, I'm going to talk through a specific example that actually arose organically when I was first designing experiments for this project. Assume that the AI is learning how it should navigate this grid world based on demonstration feedback from a human. And in this particular grid world, the goal is the square on the bottom right, but the highest reward trajectory actually goes to the pot of gold in the bottom middle, and then just stays there until the horizon runs out and the task ends and never goes to the goal at all. So the reward from going to the pot of gold outweighs the cost of not ending the trajectory early by going to the goal. Now, if you're human like me, goal has a semantic meaning like end or terminus. So it's natural for a human to assume that any demonstrations in this environment have to end at the goal. I specifically designed an environment like this one where the highest reward thing was to go somewhere other than the goal. And then I went off and did some other work. And when I came back later to generate the human's choice set, I just automatically generated all paths that ended the goal, therefore omitting the most effective path. And if the AI doesn't know this thing about humans, not only will their model of the human's choice set be misspecified, but in a case like this, it can lead to really poor inference. Here's what this looked like in my experiments. The human choice set is the set of green lines in the grid world on the left. It includes only trajectories that end on the goal, which again is the square at the bottom right. The choice set that the AI thought the human had is the set of lines on the right. And it also includes the highest reward trajectory. That's the blue line on the left side of the graph. It never reaches the goal, but it also manages to avoid all of the red squares, which is great because those are lava. And since it avoids all the lava, it's actually the highest reward trajectory in this particular grid world. So the choice set that the human actually chose from and the choice set that the AI thinks that the human chose from are nearly identical. The only difference is that the robot choice set is one extra trajectory that the human's goal bias rules out. However, this slight subtle misspecification has a really big impact. Assuming that the human is rational, they're going to choose the path from their choice set that encounters the least amount of lava, which happens to be the one on the left here. The AI observes this piece of feedback and then updates their belief according to this update rule, which formalizes basically what I described earlier. Given that feedback and the AI's misspecified choice set, the AI ends up with this posterior belief of reward models. That's the graph in the lower right. The blue dot on the graph is the ground truth reward model that the human has. And the green dot is the peak of the AI's posterior belief over what reward model the human has. Not only is the inferred reward really far away from the actual truth in this case, but it also means that the AI believes it should be essentially indifferent about lava, when in fact, according to the human, lava is very, very bad and should be avoided. As you can imagine, this led to very poor generalization when I tried to run this agent in other environments. In this work, we empirically and theoretically distinguish different types of choice set misspecification that correspond to different types and severities of error. For example, some correspond to being overconfident, but essentially correct about the reward. Some correspond to being underconfident. Some correspond to just being totally off base. A significant and kind of surprising finding is that some classes of misspecification lead to particularly bad errors, where others are actually neutral. So not all misspecification is created equal, and it's quite valuable to know which type of misspecification you have, because it can indicate how bad it is. Since the classes are defined by two structural dimensions of the relationship between the human and AI choice sets, they can be arranged spatially where neighboring classes differ along only one axis. We conceptualize this as a landscape of misspecification, where agents can move to neighboring classes by getting more information from the human or otherwise changing aspects of their choice set, which is great because it means that it suggests ways that the AI may be able to learn to navigate this landscape and move from more harmful types of misspecification to less harmful types. They're improving reward inference, which is the ultimate goal here. We'll discuss this landscape. Okay, so here is our classification. I'm not going to go through it properly here because I don't think I have enough time, but I can come back to this later if people are interested, or please check out the paper or ask me more about this later if you'd like. I'll just briefly say the two axes along which these types of misspecification differ. The horizontal axis is the relationship of the, here I'm calling them agent and expert instead of AI and human, because I wanted it to be a little bit more general. But the relationship of the AI and human choice sets, either the human choice set is a superset that completely contains the AI choice set, or the AI choice set is the superset, or neither is a superset of the other and they overlap. That's the horizontal axis. And the vertical axis is where the optimal piece of feedback is. Is it in both choice sets or is it just in one? And now here's a rough evaluation of these classes. The worst inference occurs in class B3. It's actually sometimes possible for the agent to update directly away from the ground truth in this class, whereas that's not possible in any of the other classes. In contrast, classes A1 and A2 are provably neutral. In expectation, they neither benefit nor hurt inference, though of course in specific cases they can benefit or can hurt. It just averages out over all possible cases. Each of these classes is a location on this landscape of choice set misspecification. As I alluded to a moment ago, the next step for this project is to work on techniques for an agent to identify its location and navigate around this landscape. Under some conditions, it could be possible for an AI to realize that it might be in a really bad class. For example, if the piece of feedback that the AI gets is super irrational under any of the possible reward models that the AI is considering, then that could be reason for the AI to reason, I think I must be missing something here. I should get some more information from the human. And by actively querying the human to say something like, hey, are you considering this piece of feedback? Or how large is your choice set? The AI can get more information about the human's choice set, update its own, and therein move around on the misspecification landscape. Techniques like this could improve all kinds of reward inference that involve the human giving feedback from an implicit choice set. So that includes inverse reinforcement learning, inverse reward design, pairwise comparisons, lots of other modalities, commonly used modalities of feedback. This project uses the unifying formalism for reward inference that's presented in the paper, Reward Rational Implicit Choice. So if you're curious to hear more about that aspect, I recommend checking out this paper. And I also wanted to highlight this other paper which came out in the last 6 months or so, which builds on our work by designing agents to systematically underestimate the size of the human's choice set, which tends to bias them towards less harmful forms of misspecification. They also do some experiments with human participants, which I found to be interesting. In conclusion, the common framework for reward inference is vulnerable to choice set misspecification, but this misspecification can be classified in a way that predicts the type and severity of errors in inference. And in the paper, I have many more details on this classification, what I mean by type and severity of errors, and the specific experiments that I ran to evaluate that. This suggests methods for AIs to identify the type of misspecification that they have and to navigate the landscape to less harmful classes by actively querying the human. I'd like to thank my collaborators, Rohan Shah and Anka Dragan, as well as the rest of CHAI for feedback on this work. And I'd like to thank you guys for listening. Are there any questions?
Hi, Rachel. Thanks for a very interesting talk. I was wondering if you know of efficient methods to find, to root out those misspecifications. Like, you know, I remember in one of your charts you have a blue trajectory. I mean, without really playing out all these possibilities, how? I mean, let's assume I mean, the human has assumed that the agent has encoded their specifications correctly, but I mean, what would be an efficient way to find those specifications, misspecifications?
Mm-hmm. In answer to your question, I don't know of any efficient way to find these misspecifications. This is honestly an entirely new direction. This paper is proposing this definition and classification of misspecifications. So I think the next step would be to try and come up with efficient methods for agents to algorithmically determine, or even communicate to the human some type of information that will allow the human to efficiently determine whether there's some sort of misspecification going on. But this is ongoing work and I haven't gotten there yet, and I'm not aware of other work in this vein, aside from the piece with the human experiments that I mentioned at the end.
Thank you.
Thank you.
Okay, well, that was absolutely awesome, Rachel, this new line of work. I think we can have additional discussion, you know, in the discussion panel. So let's move on here to ethically compliant planning and moral autonomous systems. So,
hi, can you hear me?
Yes, hi, Samir.
Okay, perfect. Okay, so sorry, actually, give me 1 second here. I'm going to, that's fine, actually. Okay, so my name is Samir Nashid, and I will be talking about ethically compliant sequential decision-making today. Basically, so value alignment is a concept where, you know, basically a program is not coded to do what the developer intends it to do. We've probably all experienced this at some point where we write some code and we think that we're specifying one thing to happen and something else happens. So usually the term value alignment is used when we are trying to encode something about how we want the agent to behave in the world with respect to other people's lives. Ethical theories are sort of offer a guiding principle for a scalable application of rules to guide how we should design different systems. However, they're super hard to implement. We've obviously they've been studied for thousands of years. I mean, people have been trying to implement them for decades, and we still don't really quite understand how to do it in a tractable way. And one reason for this is that developers often implicitly balance safe behavior with efficient, like, task completing behavior. So this is a point of contention. A lot of reward functions are specified where they're actually combining things which maybe shouldn't be combined. So for a typical decision-making process, you have a task, you model it with a decision-making model, and you run an objective, you maximize an objective, and you get an optimal, in this case, amoral policy. It's a policy that doesn't reason about anything about the outcome of its actions other than that it's completing the task as efficiently as possible. What we're suggesting in this paper is essentially an augmentation to this idea where you also have an ethical framework that's in addition to your task. So the ethical framework is modeled by an ethical context and a moral principle, and we'll get into those in a second. And this generates what we would say an optimal moral policy, or an optimal policy that's subject to constraints of types of behavior that the developer can specify. So the main advantage of this is that it's explicitly specified in terms of the outcomes rather than specified in terms of the reward function and transition function, which is typically much harder to do. So in this paper, we're working with Markov decision processes. So I'm not going to explain them all now, but essentially you have states, actions, a transition function, which is essentially your model of the world. What happens when I take this action? What state do I transition to? A reward function that tells you how good it is to be in a given state, and an initial states distribution. You get a policy, which is basically describes what your agent is doing, with what action to take in what state. A value function, which is induced by the policy. And we usually denote the optimal policy, which is the policy that maximizes the value, pi star. So you can solve these in many ways, but one way is to use a linear programming, which is what we use. So task completion, we say the decision-making model is this given by D, which is an MDP. So this is the information you need to complete the task. And the ethical context is basically it's the information you need to follow an ethical theory or follow an ethical framework. It may not be relevant to the actual task completion. So it could contain information that is completely irrelevant to efficient behavior, but is relevant to safe ethical behavior. And then you have the moral principle, which in this case is a Boolean function that just tells you whether or not a given policy satisfies the rules you've prescribed. So this amounts to essentially a constrained optimization problem. You're trying to find pi star subject to compliance with whatever rules you've given. So in this diagram here, the whole box is the set of all policies. The green area is the set of policies which are not compliant, and the purple area is a set of policies which are compliant. So you're solving for this pi star sub row here. So okay, well, what would such a theory or these theories even look like? So there are many ethical theories. One example is something called prima facie duties. Prima facie duties is basically there are proposed many duties are inherently good. So some examples are fidelity, reparation, gratitude, promise keeping, or honesty are other examples. These are actually contested in philosophy, but how might we map these to a particular ethical framework? So one example, you can have an ethical context that has a set of duties, delta. It has a penalty function, which tells you how bad is it to violate a given duty in a given state, and some amount of tolerance that says, I'm okay with violating a certain amount of these duties in expectation. These duties may conflict, so sometimes you need this tau to generate anything at all. So the moral principle is fairly simple in this case. It's just making sure that your expected cumulative penalty is below some tau. So does this actually work? It turns out it was surprisingly effective. We asked basically two sets of roboticists and AI PhD students here to implement a safe autonomous vehicle behavior that basically needed to limit when it's speeded and under certain conditions of pedestrian traffic and other things in an autonomous driving simulation. So one task they did was to basically use this framework to implement a prima facie duties ethical context to try to induce safe behavior. And then the other task they had was to generate the same identical behavior, or they tried to generate the same behavior, but to do this by just modifying the reward and transition functions. So in this graph, you see that the ethically compliant framework was always safe. It's always in the green region in expectation. And it's also as efficient as possible. In the red diamonds are basically the MDP modification, the direct modification of essentially the task description. And so you see many examples in the red, which would be not in compliance. And so basically if you are in the lower left, you're too conservative, your modification to the policy didn't result in efficient behavior. And if you're in the upper right, you're too aggressive. So the spread in the x-axis of the PFD implementations is because it's relative to, we're graphing it relative to the policies generated from modifying the MDP. So when you're giving a very aggressive policy, it's very fast. It will result in a relatively slower but still safe PFD implementation. So to conclude, basically, we also have an open source library. You can play around with some of these things as a visualization and as some startup code. So you can play around with these different specifications, and you can see the difference between the different types of policies that get generated. So that's all I have. Thank you very much. If you have any questions, I'd be happy to answer.
Thank you, Samir. Any questions for Samir? You know what, we're running a little late, so let's save any additional questions for the discussion panel. But yeah, so let's move on here to the next talk, and that one is aligning with heterogeneous preferences for kidney exchange, again by Rachel Friedman.
Hey, I'll go ahead and share my screen again. Sorry, one moment. There we are. All right. Hello again. Now I'll be presenting on my paper on aligning with heterogeneous preferences in kidney exchange algorithms. This is different from my previous work. This is a multiple to single alignment problem where we need a single algorithmic decision maker to make decisions on behalf of an entire population of humans. Kidney allocation is a particularly interesting domain for studying this preference aggregation problem because human participants can have highly heterogeneous preferences over who should be prioritized, but because it's implemented by a public health system that's automating life or death decisions, it's a legal requirement that there just be a single policy that applies to everyone. So that's how we get this real world example of the multiple single value alignment. First, I will briefly explain and motivate the chosen domain, which is kidney exchanges. Then I will discuss the challenge and significance of preference aggregation for value alignment, and finish with an overview of the methodology I propose here and results from simulated experiments that I've run. So first of all, what is a kidney exchange? Okay, so imagine that you have kidney disease and you need a kidney transplant. You have a friend who's willing to donate a kidney to you, but you're medically incompatible with them. Maybe they have the wrong blood type. Typically what this means is that you have to join the waiting list for a kidney from a deceased donors, but demand for those far outstrips supply, so you may be on the waiting list for years, and during this time you even be put on dialysis. So this is really not a good outcome for you. Now imagine that I am in the same situation. I need a kidney transplant. I also have a friend who's willing to donate to me, and we are also medically incompatible. But if my friend is compatible with you and your friend is compatible with me, then we can exchange our kidneys. My friend donates to you on the condition that your friend donates to me. Kidney exchange matching markets facilitate this on a broader scale. There's actually hundreds or thousands of pairs like this that participate in national kidney exchange matching markets in the US and the UK and several other countries. If we represent each of those pairs as a node in a graph and draw a directed edge from node A to node B, if donor A is compatible with patient B, then the problem of forming exchanges like this becomes the problem of finding disjoint cycles in this graph, which we know how to do efficiently using linear programming. For example, here is almost the highest cardinality set of cycles in this particular graph. The really interesting thing here is that the largest public exchange in the US has completely automated algorithmic matching. So we have an algorithm deciding who lives and who dies in expectation on behalf of an entire population. And as you can see here, its use in the US is becoming increasingly common. In the paper, I go into much more detail about how this problem is formally stated and solved algorithmically, but I'll skip that here to save time. Returning to the set of cycles in this graph, we can see that the set of cycles actually isn't disjoint. There's one node that participates in 2 of the cycles. So only one of these 2 exchanges in red can actually take place. How should the algorithm choose which exchange takes place? They both include the same number of nodes, but they include different participants, and therefore different people are going to receive life-saving transplants depending on what the algorithm chooses. This question here is where my work comes in. Making the decision of which group of participants to save requires aggregating the preferences of many different stakeholders. There's the patients who participate in the exchange, the donors who donate, the public systems who are funding and running the exchange, and the general population who may one day have the opportunity to opt in to the exchange, because it is an opt-in system. You're not automatically enrolled in it. So the algorithm that makes these allocation decisions must make them in a way that aligns with the values of many different human stakeholders. This is the category of alignment problem that Critch and David Kruger referred to as multiple single delegation in their report on technical AI safety research directions, if you've seen that. And there are actually many different present-day instances of this kind of alignment problem. There's kidney allocation, of course, but also self-driving cars and algorithms informing bail decisions. These are all cases where algorithms must make decisions according to a single policy on behalf of many different stakeholders who tend to have widely varying preferences. Because the goal is to develop a methodology that can handle real human preferences, messy and heterogeneous as they tend to be. In this project, I used real human preference data that we got from asking humans to make faux kidney allocation decisions. In the survey I used, there are 8 different fictional patient profiles. These profiles differ in age, in drinking behavior, and health status, and each one is a short description of a patient like the 2 you see here. Survey participants were presented with pairs of profiles like this pair and asked to choose which one they thought morally ought to be prioritized for a kidney. I used this preference comparison data to build a model of survey participant preferences and then incorporate it into the kidney allocation algorithm. The team that gathered this data the Duke team that originally gathered this data used it to learn a single score for each patient profile. However, individual preferences expressed on this survey were highly heterogeneous, so I don't believe that a single deterministic utility function is sufficient to accurately represent them. Instead, in this project, I use an economic model called BLP, which learns a distribution over utility functions instead of just a single one that's approximately something like the mean. So it learns a distribution instead. And again, I describe how this model actually works in the paper, but will not go too far into the weeds here. But here's how we use it. Each time a new patient-donor pair joins the exchange, we sample a utility function from the BLP distribution for that pair, and then use it to weight outgoing edges. So for example, if the BLP function 3 at the bottom heavily weights the recipient's age, and patient 1 is young, while the patient in node 2 is old, then the edge from vertex 3 to vertex 1 will have a higher weight, whereas the edge from vertex 3 to vertex 2 will have a lower weight. And the algorithm prioritizes high weight cycles over lower weight cycles. So this means that it's more likely for the donor in vertex 3 to donate to patient 1 than to patient 2. Kidney exchange algorithms typically formulate the matching problem as a linear program like this. If you're not familiar, solving a linear program maximizes a certain value, which is the objective, subject to various linear constraints. In this example, that value is the number of patient-donor pairs that are matched, called the cardinality of the matching. However, I modify and reformulate the problem to incorporate these BLP utility values. So I make the maximum cardinality a constraint and modify the objective to maximize the sum of the BLP values. Solving this revised linear program still matches as many pairs as possible because of the cardinality constraint, but breaks ties by prioritizing matchings that are preferred by the sampled BLP utility function, which means that there are participants who took the survey who preferred matching patients of that profile. To evaluate the effects of this, I built a simulation and simulated 50 runs of 5 years worth of daily matching using 3 different matching algorithms. The first matching algorithm just weights all potential kidney recipients equally, regardless of their profile or how much they are preferred. So this is just kind of like a lower bound baseline. The second does what the Duke team did. It weights recipients according to a single utility function that kind of averages across all of the preferences expressed by human participants. From here on out, I'm gonna call this algorithm homogeneous. And the final one weights donor-recipient pairs, which are edges in the graph, according to the BLP model that I just described. And I'm gonna call this one heterogeneous. I hypothesized that the heterogeneous algorithm was going to best represent the diversity of stakeholder preferences and therefore would lead to matchings that are on average higher in survey participants' rankings over patient profiles. And note that higher ranks have lower numbers. So being ranked 1 is better than being ranked 4 is better than being ranked 8. And here are the results. These are the average ranks of all patients matched by each algorithm. The top algorithm is, so the top is heterogeneous, the middle is homogeneous, and the bottom is equal, with heterogeneous being the one that I proposed here, and homogeneous and equal being 2 different baselines. Going from the bottom, the equal algorithm has an average rank of around 4.0, which is the same as the average rank of all patients, because there's 8 different profiles. The homogeneous algorithm improves that a bit to 3.7, and then the heterogeneous algorithm further improves it to 3.2. So the proposed heterogeneous algorithm that uses sampled BLP values appears to substantially better satisfy the diversity of preferences in the community of stakeholders than the homogeneous algorithm does using the single utility function, or the equal algorithm, which doesn't take preferences into account at all. And so it's intuitive that that one would perform worse. But I think it's notable that the heterogeneous also performs significantly better than the homogeneous. And what this graph shows is the proportions of patients of each profile type that entered the exchange and were subsequently matched. There's 8 different profile types. Those are along the bottom. The green boxes are the homogeneous algorithm, and the blue boxes are the heterogeneous algorithm that I've proposed here. And the first 3 types on the left are the ones that are the most heavily preferred and most frequently matched. By looking at those 3 types on the left, we can see that both the heterogeneous and homogeneous algorithms advantage them, but the heterogeneous algorithm does so to a lesser extent. Basically, the blue boxes are usually a little lower than the green boxes. This makes sense, actually, because the heterogeneous algorithm will occasionally sample utility functions from the BLP distribution that disadvantage these profiles, while the homogeneous algorithm will only ever use the single composite utility function, which ignore these minority preferences. So essentially, the heterogeneous algorithm allows minority preferences to occasionally be expressed, whereas the homogeneous algorithm never does. In this way, the proposed heterogeneous kidney allocation algorithm better aligns with the preferences of all stakeholders, even the outliers, while still allowing the system to be fair in that all people who enter the exchange are being matched by the same algorithm. I would like to thank the Duke Moral AI team for sharing the human preference data, Professor John Dickerson for an early version of the kidney exchange simulation, and Yunhao Huang for help and suggestions on this project. And again, thank you to you guys for listening. Are there any questions?
Rachel, thanks for your presentation. I don't know if I might be tired. It's already almost 10:30 here, but I couldn't stop kind of thinking about how this might apply to matching vaccines to different groups of people.
Yeah.
COVID vaccines, you know, I know there's a lot of debate who should receive the vaccine.
Mm-hmm.
Do you think this work could apply to making, you know, the best decision in terms of who should receive the vaccine? Could this be applied to that kind of problem?
Mm-hmm. That's a good question. So a constraint of this algorithm is that the same number of people get matched. It's just switching around which people get matched. And I think that applies to the vaccine case as well, where ideally we're still going to use all of the vaccine doses, but we might shuffle around who gets doses in the first wave.
Yeah,
I
guess questions how to capture preferences, or, you know.
Yeah. Honestly, yeah, I can see that. We could get together a large and hopefully representative sample of the general population of a country, and then come up with a bunch of different potential profiles of people who could receive the vaccine, like age, health status, whether they're care workers or not, what their living situation is, and then ask people what their preference, give them a bunch of dilemmas who should receive the vaccine, and then try and extract out a distribution of utility functions, again, based on that. Something that I think this work, another step that needs to happen in this work before it's implemented, is I think there should still be some allowance for top-down control. So we have this sort of bottom-up, using machine learning to extract out human preferences from a bunch of survey data, which is great. I think we should still have some amount of top-down moderation where we take in ethicists and policymakers and domain experts and allow them to moderate the utility functions that this method comes up with. And I think we need a really good methodology for doing that before we use something like this for such a critical
providing knobs, I guess, like tuning knobs to decision makers.
So like, this is what the people want. Is this okay? Do we need to change this at all? Are they missing something, kind of thing?
Yeah. Thanks, Rachel.
Thanks.
So I have a question about meta preferences. So might it be an issue if there's so much idiosyncrasy from one patient within a type of group to the next? Might they feel like that is unfair in and of itself?
Unfair because we're sampling from the distribution of utility functions each time. And even though they're all getting sampled from the same distribution, they might get a different utility function sampled.
Right, even though it's the same program that's making the decision, they're getting a different policy applied to them, even though they're in the same class.
Yeah. There's some interesting work in the domain of kidney exchanges around fairness, because there are so many different definitions of fairness that you can apply. Under one definition of fairness, this is fair because they're same system, same algorithm. Under a different definition of fairness, this isn't fair because the system is going to sample a different thing from the distribution for different people. So yeah, basically I agree with you. There's an argument to be made that there's some important definitions of fairness that this doesn't quite meet. And then we have to trade that off against, does this better capture societal preferences, and is that worth it not being fair in some respects while still being fair in others? Does that make sense?
It does. Well, I guess a follow-up to that. In the case of meta preferences, has there been like a real-world like survey work in trying to explain different schemas of preference aggregation to people? And have their decisions on those?
I'm aware of a lot of work proposing and evaluating different types of preference aggregation, but I'm not aware of work explaining what you just said, explaining different types of preference aggregation to people and seeing which ones they prefer. That would be very interesting. It's possible that that work exists and I just didn't come across it in reading for this, but yeah, that's really interesting.
Cool. Okay, well, any other questions for Rachel?
Rachel. Thanks for the presentation. I have a question for Rachel, but also anyone here, if you have any opinions, feel free to voice out. I'm interested in your opinions in what kind of numerical methods do you have in mind to better quantify the level of misspecification? Like, I am aware that some people might use regret or something like that. I'm just curious, what's your current thoughts about this?
I'll stop sharing because it's not relevant. Yeah, so so essentially you end up with two different distributions of reward functions, the correct one and the incorrect inferred one, and you want a measure of how bad that is. And I used a bunch of different measures actually, and one of them that I used was regret. I generated a number of different other grid worlds with lava in different places, and then measured regret across all those grid worlds using the learned reward function. And I found that to be quite indicative of how good or bad performance is. I also used things like KL divergence and entropy, which is how I got ideas about how overconfident or underconfident an inference might be. And this paper I finished and submitted for the original deadline, so I guess in May. And I'm mentioning that because shortly afterwards, I'm gonna look it up right now, a paper came out with a metric for quantifying differences between reward functions that I really like. So I'm going to look that up real fast because it's something that I thought, oh, if that had, come out a couple months ago, I would have wanted to use that. Okay, it's just called Quantifying Differences in Reward Functions by Adam Gleave, and it was a collaboration between a couple of people at CHAI, which is where I work, and a couple of people at DMind.
Great, thanks for sharing.
Yeah, thanks. It's a good question.
Okay, so we're well into the panel discussion now. If there's any questions for Samer as well, or if Samer has questions for Rachel or vice versa, and of course Mauricio and Cynthia are, have the floor as well. Okay, so maybe I have a question for Samer. So do you think that your framework would apply to different types of ethical frameworks, like consequentialism, for instance?
That's an excellent question. So in the paper, we present 3 different frameworks, each modeled off of a different popular ethical theory in moral philosophy. They're not intended to be like exact. Obviously these things are all approximations of all the nuance that happens in a real theory. But yes, this approach is, you could represent any system of ethical decision-making you wanted, whether it exists already or not. It's arbitrary, you can make arbitrarily complicated ones. In fact, we have a paper in preparation now for the next IJCAI, which it does have some consequentialist theories. It also has things that are based on like contractarianism, Rawlsian-based theories, things like the golden rule. So those happen to fall into a class of theories where you are actually reasoning about the internal state of other agents. So, prima facie duties and other things like divine command theory don't actually reason about other agents explicitly. They reason implicitly about them by following a set of rules that you can apply to your own agent's actions alone. Right? You just need to figure out whether the duty applies in your situation or not. And it doesn't matter who is around you. In these other set of theories like utilitarianism, which is it's one consequentialist theory. That actually requires you to model basically every other agent that you care about in something called a moral community, which is the set of things that you have moral consideration for. So to answer briefly, yes, yes, you could basically model whatever you wanted as long as you can make it into, as long as you can design a Boolean function that is tractable. Those happen to be intractable if you enumerate everything, you basically turn everything into a big joint planning problem. But if you approximate some things, you can make it a polynomial size problem. And so you basically look through a polynomial size number of things, and then you generate a single constraint, and then you solve your original MDP, which is the same speed as normal.
And sort of a follow-up to that, it's my understanding that in your framework, the constraints are necessarily Boolean. What if they were real valued? Would that would it simply be some linear combination inside instead, or would it complicate things?
Yeah, that's a good question. Maybe I didn't cover this properly, but basically the constraint is Boolean, but the constraint could involve a real number, right? Like the example I gave was basically that your expected cumulative penalty is below a certain real number. So this could be set to whatever you want, and it, you know, the actual outcome of whatever policy happens is it's intimately related to, you know, what type of duties you define, what the decision-making model looks like, you know, what's required to do a certain type of action.
I got that, but what if we actually wish to propagate the degree of violation?
So propagate the degree, are you saying like, do you want to change it online?
No, just have it, let's say you're trying to do something a little bit more like an optimization, I guess, than simply, you know, this Boolean of whether it passed or failed.
Oh, okay. So you're asking, if I understand correctly, you're saying like, you want to be able to trade off between like following some ethical theory and not following it. Like you want a knob that you can turn between yes and like doing it and not doing it. There's some gray area in between.
Well, so like truthfulness or something like that. I mean, surely there's gray areas, and there's you know there's spectra of, you know, just how truthful are you being.
I see what you're saying. Yeah. Okay. So I think you could okay. So the cop-out answer is like, yes, you could totally define such a thing. You would define multiple duties, and some would be supersets of other ones. I think the real answer is that if you were following a specific ethical theory, there's no ambiguity. Like you know, someone would decide this statement is truthful or it's not truthful, and either the duty would apply or not. But I think you could engineer a set of duties, for example, or some other penalty. Yeah.
Sorry to interrupt. My question is more on the mathematical side than on the philosophical side. Like would that significantly complicate the formulas to try to have it be more fuzzy in that regard?
No. Like I was like, you can generate the type of behavior that you're after just by adding a few extra rules to your ethical context, basically. And no, in this case, it wouldn't really change the time it takes to compute the constraint, which is really the bulk of the time.
Yeah. Okay. Thank you.
Yeah.
Any other questions for either Rachel or Samir? I have a question for Rachel. In that landscape map of the degree of possible misspecification, I'm not sure I fully understood how that was generated, or whether that was conceptual, or whether that was like a literal output. Can you maybe go over that once more? Like, what are the vertical and horizontal axes, or is that literally an overlay map on the previous map that you showed of the you know, that grid world?
You're muted, Rachel.
Sorry about that. Thank you. Yes, I will share my screen to make this more clear. Ah, yeah, thank you. Okay, so here, I sort of showed two different landscapes. There was this one and this one. And this one is kind of just a figure to describe what I mean. This isn't literal. This is the more literal one. So this is the classification that I came up with, or that we came up with. And then these two classes, the ones that are highlighted in blue-green, are the ones that empirically were the best because they were provably neutral, which is kind of the best you can hope for with misrepresentation. And then the one that's dark red was the worst because it included the worst possible cases and averaged out over some number of dozens of experiments. It led to the highest regret and the worst other results on some other metrics that are the table in the paper. And then the other two are kind of intermediary between those. The dimensions here are literal in that A1 is related to A2, in a way that it's not related to B2. So it'd be easier to say move from A1 to A2 than it would be to move from A1 to B2. The two dimensions on which these are related, the horizontal one is, so remember you have the human choice set and the AI choice set, and these two are literal sets. They're literal sets of choices. And so these are different possible set relations. Either the AI one is a strict subset of the human one, or the human one is a strict subset of the AI one, or they intersect each other, but neither is a subset. It's also possible for them to be identical, but in that case, there is no misspecification and there's nothing to talk about. And it's also possible for them to be entirely disjoint, but if they were entirely disjoint, the misspecification wouldn't be so subtle because the human would give a piece of feedback that the agent just didn't think was possible. And so presumably the agent would see that this just wasn't possible and would hopefully realize that something was going on and revert to some known safe behavior.
And so is the figure on the next slide some abstract generalization of that? And if so, how would you characterize the navigability from one box to the next? From one cell to the next?
Yes, this is an abstract generalization of this, of the idea I was describing. Ways that one could navigate, going back here, to give a concrete example, if, I'm trying to think which one I would be most clear. Okay, yeah, so looking at A1 and A3, those are easier to navigate between because they're identical on one of the dimensions. And a way that if we were in A3, a way that you could get from there to, oh no, actually, sorry, A3 to A2. If you were in A3 and you wanted to get to A2, because we know that A2 is probably better, and you were in AI, something you could do is you could ask the expert just enumerate all of the choices that you're considering. Just show me everything that's in your set, and then I'll incorporate all of that into my set. So that's like taking the entirety of this orange circle over A3 and putting all of it inside of the blue circle, which then moves you to A2. And that's just, it's kind of intuitive that this would lead to better inference because the human doesn't, the agent knows everything that the human is capable of doing.
Got it, got it. Okay, yeah, helpful, thank you. Okay, does anybody else have any other topics they want to raise?
I had a question for Samer, maybe a bit controversial or and also obvious given the title of your paper. Have you thought about how this framework would apply to autonomous lethal machines?
Yeah, that's a fantastic question. So actually, some of the original, so you could, one way of describing this system is to say that it's an ethical governor of policies. So the term ethical governor comes from, I think, Ronald Arkin, and if you know him, he's a very involved with the military. So a lot of the current work up until a year ago basically focused on myopic ethical governance. So this is like the ethical governor evaluates decisions at a decision by decision level online. So whenever the agent's about to act, it runs through some rules and says, okay, this is an okay thing to do or not. In this scenario, we are just trying to extend this concept to sequential decision making. So it's totally applicable. Many decisions out in the world can and probably should be modeled as sequential decisions instead of myopic consideration. So absolutely, this is something that you could do. So I would like to stress that the main benefit of this is also not necessarily that you can implement an ethical theory, but that it's very interpretable. The person programming it is very certain that they're specifying to not do this. You don't have to enter a reward function and then guess what the agent will do. You can say, the agent, do not do this, or do not do this with a certain probability, and you're guaranteed to get a policy that complies with that. So totally something you could use in a military setting. Obviously, you would need to define the ethical context in a way that contains all the relevant information for you.
Yeah, I think in real life, you deal a lot with ambiguity. So how do you have a way to represent ambiguity in your framework?
So
how does your framework deal with ambiguity?
Yeah, another good question. So I think there are two types of ambiguity really in most robotic applications. We are using a model called the Markov decision process. So that is dealing with one type of ambiguity, which is action stochasticity. So this is sort of covered naturally if you use an MDP. So you don't even have to worry about it inside of your ethical framework. It's already handled by the MDP, and then whatever rules you apply to the policy via the framework are naturally going to incorporate the stochasticity and uncertainty of the world. The other kind of uncertainty is observational uncertainty. So that would be like if you used a partially observable Markov decision process of MDP. So we don't yet have a code that does this, but we conjecture that this is also possible for POMDPs. It would probably be more expensive and a more complicated algorithm, but I think it should be possible.
Cool. Thank you.
Okay, any other questions? Okay, if not, then I would say it's time for that wrap up and best paper award.
Yeah.
Huáscar,
right.
Take over from here.
Yeah, thank you very much, everybody. I think it's hard times for the conference and workshops because of the pandemic issues. I think this is one of the reasons of the attendance and also the time zones of these workshops. So, but I think the talks were really great. The yesterday sessions were great, today as well, and we will upload them, the videos of the presentation as well, along with the presentation themselves. So I think many people will be able to look to your presentation as well. So I will just in case if you want to do your vote for the last time by using this URL and this code. Otherwise, in 1 minute or 2 minutes, I will show the results. Do you want to say something else, Mauricio, Cynthia, Richard?
Yeah, I think we can leave some time for voting for the best paper.
Yeah. I would like also to invite, I don't know, for the people that don't know, we have another workshop very close to AAAI. In AAAI, the SafeAI workshop, so you are invited to attend this workshop. It will be in February, 1 month. So there are very exciting presentations there as well. I hope some things will work better, like the posters, because the poster were not working well now. They announced the poster in IJCAI very late. And I think AAAI has a very a better platform and also a way to manage things. So if there is no more, I will show you the results. Just a second. So this is the results of the Best Paper Award. So it means that Rachel, you won the Best Paper Award this year. The idea is that since this is virtual, we will announce the Best Paper Award in the website, and also we will send you at least virtually digital certificate with our signatures. Okay. So congratulations, Rachel, and your colleagues as well. Okay, so if there is no more comment from the chairs of other people, so I would close the workshops. Or if you have any last question regarding the logistics or how? No? Okay, so thank you very much, everybody. I will close the meeting.
Thanks, everyone.
Thank you.
Great work.
Bye.
Good night.
Thank you, Huáscar. Bye-bye all.